Okay, so our next speaker is going to be Lucas Ventura, and he's going to present the work How to Sign, a large-scale multimodal dataset for continuous American Sign Language.
Hello, hope you can hear me well. Okay, I'll start my presentation. I will be presenting our new dataset called How to Sign. That is a large-scale multimodal dataset for continuous American Sign Language. And my first question is, wouldn't it be great if we could click a button and this tag would be talk, would be automatically translated to sign language? At the moment, if we want to make this talk available for people that use sign language as a form of communication, we need to hire an interpreter. So this leads to the motivation. So why should we try to solve sign language translation? Imagine living in your home country and still struggling to communicate with people that do not understand your mother tongue. Well, this is the case for more than 400 million people that are deaf or hard of hearing. They usually have sign language as their first language and use it as the primary means of communication. And not all of them can read spoken languages. Having automatic systems that can translate sign language is an important key for their accessibility, especially in developing countries that do not have access to sign language interpreters. To develop such systems, we need to first overcome a set of challenges. First, it's important to know that sign languages are not universal. As spoken languages, different countries and different regions have developed their own sign language that brings with them own culture. Also, sign languages are not a one-to-one mapping from spoken languages. They have their own linguistic rules and use manual and non-manual features to convey information, and do not translate spoken languages word by word. If this was the case, it would be very easy. Sign languages is not based solely on the hands. The location, movement, and orientation of the hands are the most important part of the body when signing. Yet, there are other non-manual features, like the face, mouth, and the body positions that affect the meaning of the sentence. We can see that is important. But on top of that, in sign language, it's quite common to use spatial grounding. Well, users, when signing, will refer to objects in a virtual space to refer to special objects when signing. So we see that it's a bit complicated to translate sign language. So automatic continuous sign language understanding requires sentence-level annotation and large amounts of data. Existing public data sets are small or with a constrained vocabulary. Furthermore, only the last two are in American Sign Languages. So that's why Amanda, the main author of this work, collected the How to Sign dataset. How to Sign is based on an existing dataset, the How to, as the source of the English sentences. The How to is a public, multimodal, and multilingual dataset that provides us with the original video, the speech, and the English transcription uploaded by the users. Using the How to videos and with the collaboration of 11 American Sign Language users, signers were recorded in two different studios. First, we have 80 hours of American Sign Language videos recorded in the Green Screen Studio. And then we also have recorded 3-hour subset in the CMU Panoptic Studio. That it's a geodesic dome with more than 500 cameras, which provide us with high-quality 3D key points. If we look at the modalities provided by the different datasets, we see that not all of them are recorded in a multi-view setting. All the how to sign videos were recorded in multiple angles. The sign language videos from the Green Studio contain two different points of view, frontal and side view. Having multi-view videos allows to be visible from multiple points of view, reducing occlusion and ambiguity, especially in the hands that are very important in sign language videos. The videos in the Panoptic Studio consist of recordings of the 500 cameras. This allows of having high quality estimation of 3D key points. The English text transcription modality originates from the subtitles of the how-to original videos. We also provide the gloss of the videos. What are gloss? we can see an example of a gloss here. It's a textual transcription of the sign language using spoken language words. The glosses are closer in the temporal order of the signs. We also have post information for all videos of the dataset. We provide post information for both frontal and side view of the green screen studio. We extract the body, face, and hand using OpenPose. For the Panoptic Studio data, we provide quality 3D pose information estimated by the Panoptic Studio internal software. This can be used as ground truth for a number of 3D vision tasks. For the Green Screen Studio, the sign language videos were also recording using depth sensor. And here we can see an example of the depth. Finally, we are the only ones to provide speech audio. The speech tracks come from the instructional videos as part of the how-to dataset. In conclusion, the how-to sign dataset has more than 80 hours of sign language videos and their corresponding speech signals, English transcription, and gloss annotation. And we also provide video categories, enabling a wide range of sign language processing tasks. Given the spoken language transcription and sign language video, we can do sign language translation. But we could also do sign language production and go from text or audio to sign language video. In our case, and to evaluate the potential of the how-to sign dataset on sign language tasks and access how well members of the deaf community could understand automatically generated sign language videos, we used a subset of the how-to sign dataset to train a human motion transfer model to generate realistic videos of sign language signers using key points as an intermediate representation. Given a set of key points, we generate a realistic videos using the state-of-the-art in human motion transfer with the implementation from Everybody Dance Now. So, given the video on the left, we generate the video on the right. How do we do that? Basically, for training, as we do not have the corresponding image pairs of two subjects performing the same movements, we cannot use supervised learning with source and target. Instead, we train a generative adversarial network. Now, to do human motion transfer, we can extract the key points from one signer using OpenPose and generating a colored pose stick figures, as we see here. This is the input to our model. The skeletons are fed into the train generator, which generates the realistic video sequence in the right. After showing the generated video on the right to American Sign Language signers, they were able to understand the topic of the generated videos. We concluded that the used model was not enough for sign language video generation, as the model struggles with the hands and face, which is crucial for sign language understanding. Nonetheless, we validate the how-to sign dataset has the potential to impact a wide range of sign language understanding tasks. This will allow tasks such as like sign language recognition, translation, and production. And we hope that in the future, there will be a button, well, the how to sign dataset will allow to be a button that can translate this presentation for signers so they can understand it across the world. And yeah, the website, you can explore the available data and download it. And thank you very much.
Okay, thank you for the talk, Lucas. Any question? No questions?
Thanks.
Okay, Lucas, maybe you can explain a little bit how you plan to continue this research, because so far, now that you have the data and so on, so what are like the next steps or the future plans?
Yeah, there's a lot of work going into cleaning more the dataset as well, and also doing things with this dataset. Like now we showed that there was some problems with the face and the hands when generating these videos, but we hope that we can improve this. And also, yeah, more things that I cannot say because they're in CVPR submission. But yeah, we're happy with this dataset, and we hope that many people will use it in the future.
Thank you, and good luck with your submission.
Thanks.
So now our last talk in this session, Núria Marzo is going to talk us about detecting natural disaster damage and incidents in the wild. Thank you, Núria.
Thanks. Okay, so hopefully you're able to see my screen and you hear me well. So yeah, I will start the presentation then. So hi again, yeah, my name is Núria Marzo, and I'm here to present the work of detecting natural disasters, damage, and incidents in the wild. This is a work done in collaboration between MIT and QCRI, and was presented on ECCV 2020. And I first want to acknowledge Ethan, Dimitri, Aritro, Agatha, which is here, Ferda, Muhammad, and Antonio Torralba for all their work in this project. And yeah, without further ado, let's start. So, as you know, when a natural disaster or any type of incident occurs, for example, an earthquake, timely response is crucial and it's life-saving. However, the process remains labor-intensive and needs a lot of manual intervention. Sometimes advancements are trying to be made, for example, on-the-ground field surveys like this tool, where people can take pictures, for example, to better inform responses of emergency teams. However, the pipeline used here is not automated. So, but also there's some work in the computer vision literature. For example, this is the XV2 challenge, which introduced a new data set of satellite images for building damage assessment. And this data set contains a diverse set of satellite images across the world. But my question is, what about social media? Because when an incident occurs, for example, a flood, as you know, many people start posting on social media. However, it is very difficult right now to filter the incident just using text or hashtags, because there's a lot of noise in Twitter, for example. And also, if you want to use an image-based method, those are mainly non-existent because on-the-ground incident datasets are scarce, and if they exist, they are very limited in size or diversity. So this is what motivates our work for trying to detect natural disasters, damage, and incidents in images, where we want to first create a dataset that contains all these types of incidents, and then we want to be able to use this dataset to train a model so that this model can filter all these images to detect incidents in the wild. So with a computer vision model like this that I've just described, a humanitarian response system could look like the following. So here you see a collection of tweets, such as those that could be posted during some type of incident. And we could use our model to detect the images that contain incidents, label them, and then we could plot all these images by their location with on-the-ground insights, and automatically we could build a damage map that could inform how to respond to emergencies effectively. So this is mainly what motivates our work. And here I'm very happy to present the incident dataset, which is a large-scale dataset that contains a lot of images downloaded from Google Images. And those images have been labeled using Amazon Mechanical Turk. So at the end, what we have is a dataset that contains 43 different incidents categories, and also in 49 different places. And in total, we have 450K scene-centric images. Just so you know more about the dataset, here on the left, I'm showing a breakdown of the class-positive images and the class-negative images that I will explain shortly. And on the right, I'm showing the diversity with a 2D histogram of image count per incident and place combination. And as you can see, we try to have as much diversity as possible. However, it is not always the case, for example, because you cannot find a volcanic eruption in a parking lot, let's say. So that's why you see some blank spots here and there. So with our dataset defined, now we can create a baseline model. And note that this is a single label multi-class problem. So the standard loss to use in these cases is the cross entropy loss. What we did was use a ResNet backbone, and then we have two fully connected layers at the end, one that classifies the incident and the other that is used to classify the place. But because our model uses cross entropy loss, it's only able to be trained on class positive images. So such as those, for example, here we see an airplane accident, or here we see something on fire. But what's the problem? That when we go to the wild, our model was very overconfident. For example, it was 100% confident that this was an airplane accident, and it was 99% confident that this was on fire, which is not what we want. So what we did to resolve this problem was to collect around 700,000 class negative images, which are included in the dataset. So here you see an airplane accident, and images for not airplane accident, or on fire, and images for not on fire. That means that our first model that we trained with the cross entropy loss was essentially really a classification among positive images. So you had a lot of different types of incidents, and you could detect which incident it was. But this is not the behavior we will see in the wild. So to adapt to that, we changed the loss to a binary cross entropy loss, and then the task became more of a detection among a lot of challenging negatives. And to do that, what we did was introduce a weight vector W to penalize these class negatives. So whenever we made a prediction that was very high confident on a class negative, this weight vector had the one in the correct position, and we were able to penalize this so that we were able to train the model to not have this many amount of false positives in the wild. So with our dataset collected, now we can make some experiments to decide which model to use in the wild. And for that, we split our dataset into training, validation, and test. And on the left, you can see the results we get with our original cross entropy loss model that doesn't use this negative loss. And as you see, the results are not very good for high confident images. But then when we use our negative loss, you will notice very clearly here that the images that we predict with high confidence are much more correct. In fact, we can see this change in performance for all the different incidence classes, where you see here the difference between the baseline model and the final model in average precision, and there's an increase in almost all different incidents, especially those ones that have a type of vehicle, for example, bicycle, airplane, boat, or bus accident. And finally here, you can see that when we use our model with this class negative, we really see a boost in performance in our mean average precision in the test set for incidents and for places. So now that we have a model that's trained with class negatives, which is pretty robust against these false positives, then we can move from the data set and go to the wild and perform some experiments there. So in the first setting here, what we did was we downloaded 40 million geotag flicker images. And on the left here, you can see the flicker images plotted with a geolocalization. And then on the right, you can see some of these diverse images shown. So what we did first was filter by earthquakes, and we plot the images, the geolocalization of images with earthquakes, but also in red, we plotted the earthquake epicenters. Then to evaluate how well we did, we report a metric of accuracy within X kilometers, which is the percent of images that fall within X kilometers of any given earthquake epicenter. And notice here that when we filter by high confident images for the earthquake class, we get images that are much, much closer to the expected location. The same thing was done with volcanic eruptions, where we again plotted the images that we detected that had a volcanic eruption, and then we plotted in red the volcanic eruptions. And again, notice again that when we filter for high confident images in volcanic eruption, the images fall much, much closer to the expected location, as you can see in this green line here. Then another type of experiments that we did was go to Twitter and do some type of incident filtering. To do that, we downloaded many tweets related to a specific incident from the past, and then we filter by radius. And then what we did was use our model to filter all these tweets that were collected using a keyword-based retrieval. We filtered those with the ones that were high confident in some incident. In this case, it was an earthquake. We did that for different incidents, so some earthquakes and some floods, and then we filtered again using our image-based model. And as you can see here, the filtered results, the filtered case does a much better job at detecting tweets that are related to the incident. To evaluate this quantitatively, what we did was use Amazon Mechanical Turk to label all the images in all the use Amazon Mechanical Turk to label all the tweets. Finally, another experiment that we did was instant event detection, and for that we evaluated our model over a series of tweets collected from August 2017 to August 2018. And to those, we used many natural disaster tags, for example, blizzard, thunderstorm, tornado, wildfire, etc., as is here. So in this case, when we use our model to filter by earthquakes, notice that for earthquakes that occur, we see that many earthquake-related tweets start spiking right after the events. So we are able to detect these incidents just by looking at tweets from a year. So yeah, overall, we were able to create a data set with a lot of diversity that is able, and also train a model that is able to detect these incidents in the wild. Yeah, thank you so much. And yeah, any more information on the code, data, and models is available here. Thank you.
Thank you for the nice talk. Now, time for questions. And here we have the first one.
All right. Great to see the use for something good here, like also the how to sign. So non-commercial use is always very good and appreciated. I would have a question regarding the data set. You mentioned that you were looking for images from Google search. So is this Creative Commons, or is this, can you use this data set, or can we use this data set?
Yeah, good question. So I think that the data set is available to use because we made sure to remove any type of incident or any type of images that could have faces or any humans in it. So I think maybe Agatha will be able to answer this better, but you could use this data set.
But is there copyright? Because when we created the YFCC100M, that I guess you're also citing, we were super careful in only including Creative Commons images so that we could redistribute that. So even if it's copyrighted and scraped from Google, that might be in some countries causing trouble by using that.
Yeah.
So yeah, no, sorry.
I can jump in the conversation if you want. Sorry, I think. Hello? Okay. Yeah, I mean, we didn't filter the images for according to Creative Commons or any type of license. We are not actually providing the images. We are providing the links and the code so that you can download the images by yourself in case that they are still available. So that's one thing that can happen, is that the data set keeps changing, right? Because people might remove the images and then they are not available anymore. Of course, it's an important question. I think that the practice of the use of images that you find in internet to train models and so on is slowly changing, right? In the past, this was considered like a fair use, right? So because you are training models for research, everything is open, you know. Now, this is changing, right? I mean, there are more concerns around how to use the images in the internet and to what extent you are allowed to use them for whatever the research you wanna do. But the case of this data set at this moment is this. We don't provide the images, just the links.
Okay,
And,
cool,
and the
thanks.
corresponding labels, of course, so that you can manage to get the data.
Thank you. We have time for one more question. Here.
Thank you very much. You mentioned that you had to include, I don't know, 60,000, 600,000 or whatever it was, negative examples in order to control for those examples where the plane didn't crash and the bicycle wasn't torn. Can you say anything about how this relates to the positive examples? Like which ratios did you follow? Was this the same for all the different incident areas and so on in order to provide these improved model performances?
Yeah, that's a very good question. Maybe I can show the ratios of positive and negative images, which are, yeah, here. Unfortunately, this is a work that was done after I stopped working in this project, so I'm not sure exactly how this was decided, but mainly what we did was try to download many images when the performance for some of these classes was very bad. So specifically, we started with vehicles and had to try to have as many images of those as possible. But here you can see a breakdown of the percentage.
But this was more a random choice, I would say, not a particular policy that you followed. Like it was basically, if it was performing badly, the more images, the better, but it was not a strict setup as such.
Yeah, I don't think so. I think that the setup was try to have class negatives for all the incidents.
Okay. Okay, thank you.
Thank you.
So thank you, Núria, for the nice talk. Let's thank the speaker again. And this was the last talk of the session, so we are closing the session. But before you leave, Xavi has some words to say about the lunch. Thank you, Xavi.
Yeah, so thank you all, especially for the speakers and chairs, for the super perfect timing. It's really awesome. So now it's lunchtime, lunch break, and as attendees, if you want, you can get a sandwich from the bar of the computer science school, which is located over there. There's a map there, but I know that many of you know how to get there. So if you don't know how to get, just follow the crowd or ask around, okay? You can get, so when you leave the room, you get a blue sticker, like the one on the slides, and you can exchange that at the bar for your sandwich. Again, if everybody goes at the same time, it's going to be crowded, so please, there's an hour and a half time, so there's plenty of time. There's plenty of time to have the sandwich. They are super quick, super fast. Everybody has time. Okay, just don't get everybody into the bar. There's a large terrace outdoors, so you can eat outdoors if you want. If you don't want a sandwich and you don't want a drink, there are other options for lunch. You can. Andrea prepared a nice website with all the options with other restaurants. So just go to the website. There's a section called lunch, and you can look for alternatives. But these are not funded, okay? We only have sandwiches for this bar. Then later, the sessions will resume at 2:30. Then presenters for that session, please be here at 2 p.m. so we can test all the technical stuff. And that's all. See you later.
És que... Oh. Vale.
provar-ho. Puja i el provem, aviam. Vale. Però és que abans hem tingut un problema amb el Mac, per això t'ho deia. Posa-la aquí i provem directament, aviam què passa.
Quin seria el connector? Que sigui tipus USB-C. Vale.
Però aquest ara no t'entrarà tu? Sí.
Jo crec que sí. A veure.
Per aquí?
Sí, exacte. Qualsevol serveix. Vale.
Aviam si es cola. Però vaig a dalt, que no em veu la rata.
Ah. Audio sempre és problema, Audio i qual problema? Visió, quan has d'ensenyar vídeos amb àudio?
I visió, jo que faig coses de color, que és molt important que el color es vegi bé. Millor que vinguis abans a veure si el que et diu el teu PowerPoint s'assembla una mica al que et diu la presentació.
Sí, no, això té pinta de... Això s'hauria de veure taronja. No, no sé. Que es veia groc. Sí, exacte. Sí. Que era blanc. Aquell to. Sí. Sí, és de fer color. I si no sabeu reproduir el son?
Vale, el vostre ordinador deu ser aquest.
Bueno.
Vale, això hauria d'anar connectat a l'altra banda. Aquí.
Vale, desconnecto aquí. Vale. A veure, també ho passant al seu.
I necessiteu cable de red aquí? No? Vale, Vale, i així doncs aquest segueix funcionant com funcionava fins ara.
Que tu sí que potser aniria bé que passessis llavors les... Tu tens el PowerPoint de Windows?
No, en Drive.
Bueno, des de Drive que...
Ho pots descarregar des d'aquí, sí. Sí, aquest té internet i tot bé, o sigui que...
La vas enviar a la URL i tot? No. Si la comparteix, dic l'usuari i ja està. Què tal, Sí. DLBCN.
Vale, perfecte.
Sí, això és d'abans, no?
El Luís Herranz m'ha...
Pujo un moment a dalt quan el vegi punxo, vale? Així veieu que...
Obre l'àudio també per comprovar que m'arribi. Ell no té àudio, però l'altre no hi sé.
No utilitzem Dropbox, no sé com...
No, que ell, el link, posarà... Hi havia un formulari...
Sí, però no és Dropbox, és Google Drive. Si l'ha posat aquí, ara de moment aquí no...
No, ell no... O sigui, ell està pujant un enllaç al Dropbox seu. Li dic que ho pugi a Google Drive directament, millor.
És que no sé quin format que tingui. Vale, dic l'usuari. DLBCN arroba... No, perdó. DLBCN AI arroba gmail.com.
Si no li dic, també ho pugi ell a aquesta adreça, que si està...
Sí, té un formulari, si posa allà la URL...
Sí, posarà la URL a... Vale,
quan la posi sortirà aquí.
Perfecte.
Vale, has convertit? Sí. Val, perdona. Aquest? Vale, per tant el teu és molt fàcil. Des d'aquí. Només quan xerreu aquí, assegura que tens el micro a prop, vale? A vegades la gent mirava aquí i llavors el micro estava allà i... Sí? Només per tenir tendència a fer així. O te'l gires una mica, no sé. Sí? Això t'ha assegurat el... Tu també, si estàs de xer, oi?
Sí.
Si veus que, no sé, que no apunta al micro, dic els hi fas. Apunta al micro, vale?
Perfecte.
Bueno, ara els hi va repetint i ja està. Va, tu ja estàs amb Dídac. Tu estàs, Dídac? O fer les proves?
L'acaba de fer i ara estan fent ells perquè han de reproduir àudio.
Àudio.
L'Òscar està fora?
A l'àudio, aviam si t'arriba.
Què tal, tu? I tu? Ah, que bé. Ole. Clar.
Em podeu posar la meva pantalla? Pots posar la meva pantalla un moment? És que, ojo...
Perquè és tele, no és, no? No és... O sigui, no rep llum, sinó que emet llum. Per tant, si emet llum, mira, ara veus, però ara s'ho pot negar.
Mucha vida, tete, que ahí fuera. Ya está, ¿no?
Hola.
El deu ser.
Hola, Òscar, què tal?
Bones.
Vale,
Molt bé.
jo ara no sé, ara el tècnic de so ha marxat, però tu estàs aquí bé, tranquil, ho resoldrem.
Vale.
Tot bé?
Molt bé. Sí.
Hola, a la sala, sí. Sent molta gent.
Se m'escolta bé i se'm veu bé?
Ara t'ho diré. Vaig a veure com funciona la sala.
El faig parlar? Vale, crec que ara ens estan sentint a la sala.
Vale.
Tenim el...
Sí, ja m'arriba i tot.
I què, bé? No sé, vols provar de compartir pantalla? No té molt de secret, però si vols provar-ho, Òscar.
Sí. A veure, comparteixo...
Vale, senten a la sala, això tingueu present.
Vale, no diré res que no toqui.
Sí, ho veiem.
Estic compartint.
No problema.
Sí?
Doncs, Òscar, senzill.
Perfecte.
Doncs ja està, Òscar, ja hem fet les proves.
Molt bé.
Gràcies.
Doncs desconnecto i em connecto exactament a l'hora que em toca?
No, senzillament ara muteja't i para la càmera i ja està.
Vale, perfecte, no em desconnecto. Molt bé.
Sí, ja el tenim aquí col·locat.
Molt bé, gràcies, Xavi.
So it's 2:30, so we will resume the meeting. And so now we are in session 3. So we will be having the session on computer vision and audio. Just to let you know, the second and the third talk will be switched. So Òscar Mañas will speak at 2:45 and Luís Herranz will speak at 3. And we will start the session by presenting Alejandro Hernandez Ruiz from IRI and UPC, and he will present us the work Neural Manifolds and Dynamic Networks, that it's a work from CVPR 2021.
Okay. Hello. So I'm going to present you Neural Manifolds and Dynamic Networks, which is a presentation that is 80% based on Neural Cellular Automata Manifold, which was a work presented on the CVPR 2021. The remaining 20% is more of a hypothetical or theoretical exploration, because my goal for this talk is so you get a new view on the neural networks. You get a new way to see how they work or what they do. So trying to open that inscrutable black box. So first, the background. Most of we know the cellular automata, which are these programs that in each of the cells, they have a rule, and depending on whether the neighbors are alive or dead, then the cell has to do something. The cellular automata are powerful models, actually. They seem simple, but they are actually Turing-complete, which means that they can compute whatever, but the only problem is that we need to figure out which rules to put into them and what's the initial state. So they are not very practical. So some folks at Google, Alexander Morbinsev and Ettore Randazzo, and they created the neural cellular automata, which is replacing those rules by a neural network. So in more detail, what the neural cellular automata does is that at each step, it takes each cell, and then it takes a very small network, which consists of 2 fully connected layers, and then that small network predicts what's the update for the cell. And by doing this very simple approach, very simple network, you can reproduce, for instance, in this case, we can reproduce an image, but it's not only that you reproduce the image, but you can also get a more complex behavior. Like, for instance, you can occlude the image, you can poke holes, and it regenerates. So this is a very interesting model. And it was very cool for us. The other set of things that I want to talk about are dynamic neural networks. So a basic neural network is, they call it a universal function approximator. So we have this function, which is our network n, and given an input x, it gives us y, right? But what does the dynamic part means? It means that the network itself would be the output of a network based on another parameter, z, or another input, z. So if, in a bit more detail, if we get, for instance, the classic fully connected layer, that fully connected layer would be the weights times the input plus b and some activation function, and all of those parts of the network can actually be a dynamic component itself. So the activation can be dependent on z, the weights can be dependent on z, and the bias itself can be dependent on z. In many cases, though, z is just x, which means that the network will adapt itself depending on the input that you're giving it. So the dynamic neural networks family include the dynamic CNN, which is actually a mixture model, the dynamic filter networks, the dynamic routing networks, the efficient net, hyper networks, spatial transformers. I mean, you name it, even the transformers themselves can be considered dynamic neural networks. But the important part here is to recognize that they are breaking the static part of the neural network by adapting themselves. So what we wanted to do, we wanted to take the neural cellular automata and create a model to be a more universal model in terms of deep learning that could actually do more than just create an image, that could do many kind of different programs. But we also wanted the model to be biocompatible. And we also wanted to have a model that can do many things, not just one thing, not just one program. So we wanted a manifold of programs. And to accomplish so, we came up with the neural cellular automata manifold, which is you take an autoencoder network, and then that autoencoder, instead of predicting the image, it will predict a program that recreates the image. And that program has the architecture of the neural cellular automata. It has some differences, though. We got rid of the alive masking mechanism. I didn't explain that, but anyway, we adapted the model so it can actually do more than just create images. It is a broad spectrum model, so it can deal with any kind of data. We stuck to the images because it's easier to see the results. But the idea here is not that we're creating images, it's that we're creating programs. So this is the architecture. It's a very simple architecture with just a few skip connections and linear layers and non-linearities and such. It's not nothing fancy here. And what can we achieve with this? Well, we achieve a network that can reproduce image and create it a step by step. Like, for instance, here, we can see the emoji is being created from a central pixel, and this emoji is growing until it is the fully grown emoji. But also, we can create any kind of images, like, for instance, this frog here that comes from the CFAR dataset was also created using the same process, and you can also see it in the image. We have a few videos here we can see. Very fast. So hopefully you had a glance. They are very short videos, but hopefully you had a glance of how these images are being created in this space. And We also have a video here on how this cellular automata can learn. So in this case, this video, each of the frames are the last step of a cellular automata that is learning to produce a different pattern. And you can see how the cellular automata is specializing to produce the different patterns in the dataset. So this is very cool. And other thing that we explored is what we call genetic engineering experiments, because that embedding space that we have, it's like an encoder, autoencoder embedding space, but we made it a categorical embedding space. So it is pretty much like the DNA with 4 classes for each. And then we wanted to see what happens when you mix those genes. And what happens is that if you get, for instance, the average genes of these faces that have the round eyes, depending on where you threshold it, because it's a categorical encoding, depending on where you threshold it, when you mix it with the different images, then you get these different results. So, for instance, you're mixing this face with this face, and you see that you get a more or less reasonable result. And when you do the same with the big, wide open smile, you see how everything turns smilier. So it indeed is capturing somehow the underlying characteristics of the images. Although here there is another effect happening, because this categorical encoding is working as an implicit drag minimizing autoencoder, but we haven't explored that yet, so that's considered hypothetical part. And one of the things when I did this work was I was always trying to figure out, like, what's happening here? How is this even possible? So what are these networks doing? So if we take a step back and try to think of it in a spatial computing way, we can think, okay, the neural cellular automata, the original one, is doing this. It's taking a pixel in the center, and then step by step is following a path on a very high dimensional space. The dimensionality of the space is pixels by filters, even with a very small image that is a huge dimensional space. And then is constructing an image there. Of course, the trick here is that we're using a convolutional network, which is getting rid of this high dimensionality of the pixels, and it is interpreting like all pixels as being equal or similar. There is a question, however. Can we start from any point in space? Do we need to start always from a pixel? The answer is no. We don't need to start from a pixel. We can start from any random point, actually. We can even learn the starting point in that high dimensional space. It doesn't look as nice, the starting point, but you can learn it, and it will work. And can we actually use an image as a starting point for another image? And the answer is yes, we can do that. Even more, how complex can that path be? There is no theoretical limitation. The limitation is only a practical limitation. How that compares to a traditional network would be like a one-shot network that predicts, except each layer has a different space. So I guess there are a few other properties to talk about, but the main gist here is that they are actually spatial attractors. So each of these networks, each of these neural cellular automata are actually encoding a function in the whole space and is attracting the whatever thing that we are producing to its goal. But the goal doesn't need to be a fixed point. It is actually distribution of points. So depending on what we're training this can be a very powerful tool. For instance, we can learn a control manifold that you can, for instance, learn to walk and learn to run, and then interpolate in that manifold, learning how to behave in all the complete spectrum. So next, how we're doing this? Well, future work, sorry. That was it. So.
we have time for one quick question. Anyone wants to ask something? Yeah, there is a question, please.
Awesome work. Especially in the part of dynamic neural networks, I am wondering how can we backpropagate actually the changes in connections between the networks? This seems, or at least in a first glance for me, it will seem that this is not actually differentiable, so we could not optimize around this. How is this done?
Actually, they are differentiable. Like the whole thing, the whole construction of the model is differentiable end-to-end. So the model is trained end-to-end. I'm sorry, I'm trying to go really fast to the point here. So this network is here taking the embedding space, predicting some weights, and then producing the image, and then the error is backpropagated all the way through the predicted weights and all the way through the network here. So it's taking all this route, and it's all differentiable end-to-end. So yeah, you can learn that. I mean, the network can learn that. Yeah, thank you.
Listen to the speaker again, and we move to the next presenter. The next speaker will be Òscar Mañas, that will present online. I hope it's ready. Yeah, hi Òscar. So Òscar will present the paper Seasonal Contrast Unsupervised Pre-Training from Uncurated Remote Sensing Data from ICCV 2021.
Thank you. Thanks a lot. So good afternoon, everyone. I'm Òscar Mañas, a PhD student at Mila and University of Montreal. I'm very happy to have been invited to the Deep Learning Personal Symposium, although remotely this year. Let's hope next year we find ourselves in better circumstances. But anyway, today I'm going to present this paper, Seasonal Contrast and Supervised Pre-Training from Uncurated Remote Sensing Data, work which I did while I was interning at Element AI, and in collaboration with Alexandre Lacoste, Xavi Giró, David Vázquez, and Pau Rodríguez, which, by the way, is also presenting in our paper tomorrow in the afternoon session, I think. I invite you all to go see him. Okay, so first of all, I would like to start with a little bit of motivation for this work. Why remote sensing and why self-supervision? First of all, like nowadays, there are many Earth-observing satellites orbiting around Earth, providing a huge amount of satellite images every day, terabytes and terabytes of data every day. But unfortunately, all these images, of course, are unlabeled. And it turns out they are pretty costly to annotate because they require expert knowledge or expensive ground sensors. It's not as easy as telling what's in a natural image. And to reduce this need for labeled data, usually, very extended practice in the computer vision community is initializing the network from ImageNet pre-trained weights. But this is not very suitable in this case because there's still a huge domain gap between natural images and satellite images. And there's no such thing as an ImageNet pre-training for remote sensing datasets. So this is one motivation to go down the self-supervised learning route. The other argument in favor of that is that remote sensing data usually contains more information, which can be exploited for self-supervision. Information such as multiple spectral bands, not only RGB pixels, but also near infrared or other wavelengths that can be captured by these sensors that are built into the satellites. Other things like temporal information, these satellites that orbit around Earth, they revisit the same regions of the Earth over time. So we can also exploit that. Or exploiting other kinds of metadata that are also provided by the satellite, such as the geolocation of the images. So knowing all this, we asked ourselves the following question. Can we learn good visual representations from all this uncurated remote sensing data that will transfer efficiently to many downstream tasks? And here by transfer efficiently, we mean that once we initialize backbone, the network with this representation, can we use very few samples to fine-tune to a remote sensing downstream task of interest? And to answer this question, we proposed seasonal contrast, which consists of first a dataset collection strategy, and secondly, a contrastive learning method to learn from the collected data. Now, to collect a dataset of unlabeled remote sensing images, we were based on a Sentinel-2 constellation of satellites from the European Space Agency. From these huge satellite tiles, we sampled image patches following the heuristic of sampling around the most populated cities on Earth. We did this to ensure the diversity of the images because human activity tends to make more changes in the environment. And here on the bottom right, you can on the top right, you can see all the locations of the image all the locations where we sampled from. And then at each of these locations, we download 5 aligned images of exactly the same coordinates, separated by approximately 3 months, so that we can notice some temporal or seasonal changes, as you can see here on the bottom right. And then we also filter these Sentinel-2 tiles that have a high cloud coverage percentage, but this is already included in the metadata coming from the satellite, so there's no need for human effort for this. And we don't do any additional data cleaning or image selection. So this is really uncurated data. There's no need for human effort in any step of this process, well, except for writing the code to do this. But, okay, and this is the contrastive learning framework we propose, seasonal contrast. It's a multi-view contrastive learning framework. The first step is given a region location of the Earth's surface. We extract different views with synthetic and temporal augmentations. Synthetic augmentations are the data augmentation you all know, color jittering, cropping, flipping, rotating the image. And temporal augmentations basically are different images of the same location at different points in time. Then we encode all these different views of the same location using the same visual encoder, the same visual backbone, which in our case is a ResNet. And then each of these representations, we project them using 3 different projection heads into different embedding subspaces. These projection heads are, in our case, are 2-layer multi-layer perceptrons. And then once we have all these representations projected in each of these 3 different embedding subspaces, in each embedding subspace, we optimize a slightly different contrastive loss where the definition of positive pairs and negative pairs changes, so that we can enforce the representation in each subspace to be variant and invariant to different things. For example, here in Z0, in the first embedding space, we can see that all the views are considered as positives. So here we are enforcing the representation to be invariant to all these synthetic and temporal augmentations. And in the second subspace, we only consider as positives the temporal changes. So this embedding subspace will be invariant, or we hope it to be invariant, to only temporal changes and variant to synthetic augmentations, and the other way around for the third embedding subspace. By doing this, by optimizing all these contrastive losses at the same time, a little bit like multitask learning, we are actually enforcing this common representation at the output of the visual encoder to preserve the information that is needed, so it preserves the factors of variation needed to solve each of these tasks, each of these contrastive learning subtasks. And this is good because we don't know a priori the downstream tasks where we will apply this. We are agnostic to the downstream tasks, so we want to keep as many factors of variation as possible. And this is the representation we will use then for downstream tasks. So for the evaluation, we use this representation to initialize the weights of the backbone in different remote sensing downstream tasks. Here I'm going to talk about 2 of them. First one is land cover classification on big EarthNet. This is a multi-level classification problem. You can see an example of the images here on top and the different labels for each image. And here in this table, at the bottom left, we have the main results of our work. As you can see, we compare against different baselines, including random initialization and ImageNet fully supervised pre-trained weights, and then momentum contrast using temporal information. For the backbone, we use two sizes of ResNet 18 and 50. And then here on top, you see 100,000 images and 1 million images. This is the size of the pre-training dataset. And then we also test linear probing and fine-tuning, which means that for linear probing, we freeze the weights of the backbone and we only train a linear layer on top. And for fine-tuning, we update all the networks, all the parameters in the network. And finally, these percentages are percentages of label data for the downstream task for big EarthNet. As you can see, across different configurations, our method outperforms the different baselines we compare against. And here on the right, you can see a little bit more in detail the data efficiency of our method. As you can see, there's a consistent gap between our method and all the baselines across different percentages of label data. So this is not the data used for pre-training the representation, but once this representation is pre-trained, the data we use to fine-tune for a new downstream task. And it's interesting to have as few examples as possible because these are difficult to annotate, right? So as you can see, for a given percentage of label data or label budget, we see that our method achieves better performance than baselines. And for a given performance target, we need less labels to achieve it. So in general, our method is more sample or label efficient than the considered baselines. And then we also evaluated on this other downstream task, change detection on the on-air satellite dataset. This is also an interesting task because if for land cover classification, we needed our representation to be invariant to temporal changes. For change detection, we actually need it to be discriminant, right? So here with these two tasks, we can actually see if our representation has learned all these different factors of variation. And as we can see here also on this change detection task, by the way, change detection, the task consists on given two images of the same location at different points in time, as you can see here on the bottom. You have to output a binary mask with the pixels that have changed between the two images. As you can see on the table on top, we also perform better than any of the baselines in terms of F1 score. And also you can see qualitatively at the bottom that the binary masks generated by our method have higher quality and cover more of the pixels that have changed. So to conclude, we have seen with this work that we can efficiently leverage all this large-scale remote sensing data without any human supervision to label or to curate the images. Using a multi-augmentation contrastive learning framework allows us to learn transferable representations which are agnostic to the downstream tasks where we will apply them, while improving downstream performance, at least on the tasks we have evaluated on. And we'll leave also as future work the use of multiple spectral bands or other metadata that included in the with the satellite data to use all this in the pretext task. That's it. Thank you, and I will be happy to take any questions you might have.
Are there any questions for the speaker? Anyone has any question? So we have a question here. You can come with the mic, please.
Yeah. Is it, can you? Yeah, okay. So I was wondering about the prediction heads. So the ones that go from the ResNet encoder to the predictions for the contrastive learning, the violet blocks. How complex are those? What models are those?
These are two-layer, multi-layer perceptrons, just to do the projection between embedding spaces.
Okay, and do you have a sense on how the potential complexity, so how the complexity of this model affects the performance of your representation? Do you have a sense of it, even if you don't have quantitative results?
Yeah, I think for the rebuttal, we did some experiments by adding as well these projection heads. So using the representation at the output of these projection heads. And it was actually worse than using the representation before. So because our understanding is that the representation before is more general and it will be able to tackle more different downstream tasks that just this representation for each embedding subspace that's more concrete in the sense that the invariances and variances that encodes are just those that were encouraged in these contrastive laws, no?
Right.
I don't know if that answers your question.
Yeah, thank you.
Yeah, thank you.
Let's send the speaker again, please.
Thank you.
So the next speaker is Luís Herranz from CVC. So you have your presentation here, if I remember correctly. Yeah. So yes, do the present. So Luis will present us a paper from CVPR 2021 that is Slimmable compressive autoencoders for practical neural image compression.
Okay, thank you, Javier. Good afternoon. Yeah, I'm going to talk about our work in... okay. Now it's okay, no? Okay, so good afternoon. I'm going to talk about our work in neural image compression. In particular, I'm going to focus on this paper, but I will also introduce the context of the line, the broad line in, towards practical video neural image compression. So the problem essentially is that we need to transmit an image through a digital channel. So we need to map an image to a bit stream, binary stream, and then the receiver will decode the image. So we are going to try to send as few bits as possible. That's low rate. Then we want to reconstruct the image with as close, in terms of error, in this case, mean square error, to the original image. Well, that's what the traditional codecs do. Now with the emergence of deep learning, there's this new paradigm, neural image compression or learned image compression, which basically replaces the traditional handcrafted codecs, where like researchers, engineers craft some very sophisticated coding tools and syntax by essentially deep neural networks. And now the game changes to train those codecs, because now the encoder and decoder are parametric and the parameters are learned. So basically this is the idea. We use a data set, we use a distortion loss, and we use a rate loss on the bit stream. And this is essentially the loss. We have a hyperparameter, lambda, that controls the trade-off, how much we want to emphasize rate or distortion. No? So that's the essential trade-off. You see some example here. In general, you have a rate distortion curve. No? So in one extreme, you have the low rate, where the lambda is low, and so it's emphasizing having low bits per pixel in this case, but the distortion is high, as you can see. Similar, on the other end, with a different lambda, you get a different, well, more emphasis on quality, on lower distortion. You can see that in this curve, each of these cases are different codecs because they have been trained independently with different lambdas. So you want to realize variable rate, for instance, with 4 different rates, you need to train 4 different encoders. So that's a problem. We need to train a lot, very costly, and also in terms of memory. If you want to deploy this in a system, you need 4 times or more if you want more possible rates, memory. So this is the first problem we want to address. It's a practical problem for practical applications, for instance, for video compression. So here we ask what is the needs. So we have neural image compression. We can optimize rate and distortion, but they are not going to be adopted unless we make them practical. And what limitations we have right now? Well, I just introduced the first one. We cannot realize this variable rate. We address this problem in one paper, modulated autoencoders. But still, that model has problems in terms of that the encoder and decoder are essentially deep neural networks with a lot of parameters that require a lot of memory and computation, and of course the latency, the coding latency will be high, and so on. So we address this in the main paper in this presentation, presented in CVPR. And we also consider other practical considerations, such as how to adapt codecs to a particular domain, and issues of compatibility, and related to some machine learning concepts, such as domain adaptation or continual learning. So we also presented this in a workshop, in the compression workshop in CVPR. Okay, so just quickly introduce this idea of how can you realize variable rate with a single model. So in a paper, the one they actually introduced, the compressive autoencoder framework, they use this trick, which is essentially the same that you have in traditional image and video coding. That is, you scale the representation before the quantization. So then you can control how many bits are going to be 0 or and so on. We observe that this can realize this variable rate with one single model, but it's not flexible enough, especially for low rate, has a drop in performance. So we propose to modulate also intermediate features and learning the modulation parameters with a small network. No? This idea is the idea of the modulated autoencoder, basically. A concurrent work, the conditional autoencoder, proposed something very similar. So now we have the variable rate, but we still have the problem of high memory, high computation cost, and high latency. So that's what we address in the Slimmable compressive autoencoders, which is basically motivated by that need, but also by this crucial observation, is that if you train a model with a certain capacity, here is defined by the number of filters per layer, in this case 192, then we train a number of independent models with different lambdas, we can get this curve. If you do the same but with a lower capacity, with fewer filters per layer, then you get this curve. So what we observe here is that beyond this point, lower rates than at this point, actually having this additional capacity is not providing additional gain in terms of rate distortion. And we observe that this is also consistent. So basically, there seems to be like a minimal capacity you need for a particular lambda or rate, but you are not going to benefit from the rest. So that's what motivates the Slimmable compressive autoencoder, based on that the smaller the model, the lower the memory, the lower the computation, and the lower the latency. So basically, the idea is that instead of modulating the features, we are going to slim the network. This is based on the idea of slimmable neural networks. And in this case, for mid rates, especially for low rates, we can save a lot of memory, computation, and latency. So that's essentially the idea of this paper. I'm going to give you an idea of the performance in terms of rate distortion, computation, memory footprint, and latency. So this is the curve that you will get with these independent models. Each point here is a different model. We chose the minimal capacity para get to the optimal. But the problem here is that you have to train these 5 models, and then you have to store all of them. So the total memory would be the aggregated memory. With the scaling method that I described before, the modulated autoencoder, our previous work, and the conditional autoencoder, which is essentially the same idea, you can see that you can achieve with one single model the close to the optimal, except for the scaling that you can see for low rate is not very, has some drop. But in terms of computation, memory footprint, etc., and latency essentially remains constant. In contrast with the Slimmable compressive autoencoder, we can gracefully adapt the complexity only to just enough to realize this rate distortion point. So that's basically the idea. And I want to mention just quickly this other work in this context of practical considerations. So here the idea is to try to adapt to customize your codec to your particular domain. So one thing that is obvious, I don't need to explain, but a codec is adapted to the domain that it has been trained with, no? But if you use it, for instance, one codec adapted to faces to encode street images is going to be suboptimal. So that's basically the idea. So what we try to do is think like, let's say that you get a smartphone or a camera and you have like an off-the-shelf codec. It's not going to be optimal to your case. Maybe you are going to collect images, or if you have a automatic photo booth or whatever, you can improve your codec with those images that you are capturing from that specific domain. The same for autonomous driving, pick your scenario. The problem is that usually you don't have enough data to train it yourself. You don't want the customers to train their own codec, and so on. So what we propose here is essentially domain adaptation. In this case, would be codec adaptation. So you have like an off-the-shelf codec delivered with your camera, and then you want to adapt it. Okay, so this is one of the scenarios. And another scenario is when you want to have like an off-the-shelf codec, then you save images taken with that version, but then you adapt it to a different domain. What happens now? That now you want to decode the image, but what happens is that the function has changed, the decoding function has changed, and even the latent space has changed, so they no longer can communicate. So there is this problem of forgetting, which if you are familiar with continual learning, this would be the catastrophic forgetting, but here is really catastrophic. So this is the problem we address here, the two problems. So yeah, and also forward. So yeah, here you have the links. We have a longer talk if you're interested in these topics. Yeah, and thank you. These are the authors. Faye and Sudeep are the main authors in the different papers. So yeah, thank you.
Are there any questions for the speaker? Someone has a question? No? If not, I can ask. So you are looking now at this getting smaller
bit streams?
Smaller bit streams and all this. So I've read some articles that says that now streaming is really cost-consuming and computational expensive in terms of this transmission. So are these models already good enough for improving this real-life transmission of streaming and all these problems, or do you believe that there is still a long way to go on this line?
Okay, so your question is if this time of paradigm is ready for adoption versus the traditional codecs, no? In particular for streaming and the cost. Yeah. I don't think so. That's the motivation for all this direction. We are trying to get there, because the codecs, the traditional codecs, you can think of JPEG or MPEG or HEVC, VVC, etc. They are based on linear transforms, which are very efficient, and very efficient decoders, and so on. So essentially, the whole thing of having very deep neural networks is increasing the cost significantly. So we are looking into how to try to, so that's the motivation that there is a lot of research now in image compression, video compression with neural networks, but it seems that the practical aspect is a bit overlooked. That's why it's not really adopted in practice. So that's just what you are.
Yeah.
Yeah, so we are working on it.
Okay, is there any other question from anyone in the audience? No, if not, we can just thank the speaker again. Speaker is Dídac Surís, that comes from Columbia University, and he will also present a CVPR 2021 paper on learning the predictability of the future.
Thank you. Okay. So today I'll talk about predicting the future in video and about how predictable the future is. And this is joint work with Rochelle and Carl Vondrik. All right. So first of all, I will show you a couple of video clips, and I will ask you to predict what will happen next. You can just say it out loud or just think it, I don't know. This is the first one. Can you see it? It's like a little dark. Okay. Anyway, hopefully you're thinking, well, this guy, Gerard Piqué, is going to sit down, and this is what's actually happening. So this is an example of future prediction that's actually pretty easy, and we can be pretty certain about it. Okay, what about this one? Yeah, so anyway, this one's a little bit harder to predict because there's some uncertainty, right? So basically what I wanted to show with these two examples is sometimes the future can be certain, sometimes the future isn't certain. And in our work, what we want to do is we want to train a model to predict the future in a video. But we want our model to be able to handle these uncertain cases, basically. Specifically, oops. Well, there you go. Specifically, we want to do it in a self-supervised way, which means that we are not using any human labels. So basically, the model is learning just from looking at video. And in the literature, this usually works something like that. There is a video, which is a series of frames. And then there is a representation space that's a space where the videos get encoded to, and we represent every video as a point in that space. Usually, the space is an Euclidean space. And specifically for future prediction, we divide the video in like the past and the future. So the past frames would be the red frames. The future are the blue frames here. We encode the future frames to this representation space using a neural network. And then the task is, okay, we ask the model to predict that point, which is the representation of the future, given the past. So predict the future given the past. Now, the problem is that when there is some uncertainty in the future, and let's say that there's, instead of one possible future, there are multiple possible futures given the past. So like, you know, this is maybe the video that we saw, and that's one of handshake, the other is like high five, and so on. There are multiple possible futures. If we try to minimize, during the prediction, we try to minimize the distance to the target, the average prediction, let's say, so the prediction that will minimize the error is the average of all the possible points. And sometimes this works, sometimes that's fine. But in general, we don't like that because that red point there, which is the optimal prediction, is not giving us any information about uncertainty. It is not giving us any information, or not a lot of information about the specific blue points. It is not giving, like, this red point may not even be like a specific action itself. So we need a better approach that lets us handle uncertainty. And in order to motivate that approach, what you can realize is that while we cannot predict exactly whether this will be a handshake or a high five, we can definitely predict that this will be like a greeting, right? So we can be pretty certain about this prediction. So what we did here, like I did here actually, is I just kind of predicted a more generic word, because if we are not very certain about the specifics, we can just go and predict something more abstract. And like in a way, like greeting is an abstraction of handshake and high five, or handshake and high five are specific versions of greeting, right? And we can generalize this and think of it as a hierarchy, where the more specific concepts are at the bottom of the hierarchy, like the leaf nodes of a tree. And then ideally, we want to predict, if we're very confident, we will predict at a very specific level of the hierarchy, like high five, for example. But if we're not very confident, we can always go up levels in this hierarchy until we are confident. For example, like the fourth level from the bottom, there's greet there. And you know, it's a more abstract prediction, it's more generic, not as informative, but we can be pretty confident about it. So what we learned from this is that ideally we want to encode these video representations as a hierarchy. And if we try to do that in the previous representation space that I drew before, which is Euclidean space, well, it turns out that Euclidean space is not very well prepared to embed hierarchies. There's always some distortion. Let's say that the Euclidean space doesn't have the right structure to encode hierarchies. And instead what we propose is to embed videos in the hyperbolic space. Hyperbolic space is a space like Euclidean, but with like different geometries, like the different space, different distance function. Otherwise, it works similarly. And a little bit of intuition about it. Basically, we can represent hyperbolic space as a disk, or like as a ball. If it has more than 2 dimensions, let's imagine it as a disk, where the edge of the disk represents infinity, and then the origin, like the center of the disk represents the origin of the space, and the distances between points in this disk are computed by this equation here, and they basically get larger and larger as we get closer to the edge of the disk, so they grow exponentially. And then here we can embed a tree. So there's a tree painted in like that disk. If you can see, like there's a tree where the root of the tree is at the center of the space, and then the leaf nodes of the tree get closer and closer to the edge of the space, and that tree has very small distortion. And so therefore, like this space can actually embed hierarchies. So now what we're going to do is do exactly the same as before. We have our video, we have the future, we have the past, we have our space. We embed the future in this space. We can also embed the different possible futures given the past, so all the possible options given that red frame. And we train using a loss. In this case, it's a contrastive loss, kind of pretty standard in the literature. If you ignore this term here, which is kind of a normalization term, this is just minimizing, on average, it's minimizing the distance between the prediction and the target point, so that's what we want to do. And again, the optimal point here will be the point that minimizes kind of the mean of all these possibilities, exactly the same as in the Euclidean space. But now in hyperbolic space, the mean actually is a little bit more interesting than in Euclidean space, because the mean of all those points, if you compute it in the hyperbolic space, you get that point over there. And that point over there has actually some nice intuitions. Kind of visually, you can see that it contains all the possible futures. But also, there are some other nice intuitions. For example, if that, actually people on the Zoom cannot, I'll just start it here. So if this prediction was closer to the origin of the space, it would contain more possible futures, and therefore it would be more generic. And if the prediction is more generic, it means that we are less certain about the prediction. If the prediction of the model was closer to the edge, it would contain a fewer number of possible futures, which would imply that the model is more specific and more confident in the prediction. Should have, yeah. Also, another kind of interesting intuition about that is again thinking about in terms of hierarchies, where the leaf nodes of the hierarchy, so the bottom level of the hierarchy, would get closer to the edge of the point kernel, which is the disk, and then the parent nodes of the hierarchy would get embedded closer to the origin of the space. So overall, this is to say that hyperbolic spaces are giving us for free, just by training the same way we would do in an Euclidean space, they're giving us the right structure to think in terms of uncertainty. If the prediction has like a small radius, so it's closer to the origin, the model will be very uncertain. And if it has a large radius, it will be pretty certain and confident about the prediction. And this comes, again, for free just from the structure. So after this, we train few models on different data sets. Here on the right, on the left, I'm showing you the input video. The model gets to process this recursively, so kind of gets to see the video bit by bit, and then at every time step, it makes a prediction. Here at the bottom, showing like the uncertainty measured by the radius of the prediction. And you will see that as more time, like time goes by, the model will get more and more certain in its prediction. And there at the right, I'm showing the class predictions that get more and more specific as the model gets more and more confident in the prediction. In this case, the task is the same task I asked you to do, which is predict what will happen next in the video. And in this case, those classes, these are not used during training. This is just like a downstream kind of classification to evaluate the model. I think there's another video. Again, as time goes by, the model has less uncertainty, and the predictions get more and more specific. All right. So yeah, so that's it. If you want to see figures of architectures and neural networks and so on, I can also show them. But thank you.
Is there any question for the speaker? a question there.
Thanks. Really cool work. So my question is about, because you presented a neat hierarchy, right? Like assuming that this can be modeled with a tree, but actually, like different actions belong to multiple categories, right? So for instance, you had hug as one of the possible ways of greeting, but hugging someone can also be a way of providing comfort, for instance. Not really greeting, but a different, so it would be in a different branch of the tree. So have you thought about that? And yeah, what would be your solution? Thanks.
Yeah, so the kind of the good part about working in with self-supervised data is that you don't have to specify those categories. In a way, the model will learn them if it needs them or if it sees them in the data. So that's something that we don't have to define. And then how can the model deal with different branches of the hierarchy? Well, it's not clear, but the model has different dimensions. So like the dimensionality is the model is not 2. So it's not like a 2-dimensional tree. It has like in practice 256 or whatever. So every dimension can open a new branch, or like every 2 dimensions can open a new branch, if you think about it. So the model has capacity to do that. It is hard to visualize, and it's hard to reason about it. So it is unclear whether or not the model is doing that, but the model has the capacity to do that. Yeah.
We have a second question here.
Congratulations for your work. I really liked it. I have one curious question, which is kind of like regarding the motivation. The hyperbolic space thing, like representing video, like how did you came up with this kind of approach? Like, what was your motivation behind,
So there's been some work with hyperbolic spaces where it usually works when you have a hierarchy. You can have, in this case, work with hierarchies of actions that I don't think has been done before, but there's other hierarchies, like, for example, hierarchies of classes like the one that we showed before, like duck is a part of animal and so on. That has been done before in a supervised way, so people annotate the hierarchy of images, and then they project that to this hyperbolic space. So this has been done before, a little bit in vision, mostly in NLP. We just kind of thought that it could work for future prediction too.
We have time for one more question. There is one question.
Hi, really cool talk. So I have a question. You were talking about a downstream classification task. And I wonder if you compared the performance of your classifier, I guess informed by your modified loss and modified specs, compared to the performance of more traditional methods.
So the main comparison here would be with respect to Euclidean space networks, because we don't really modify anything else. I think I have, oops. There's like numbers. It works better for tasks that require predicting the future, in which there is uncertainty. If you try to apply this to tasks where kind of by construction there is no uncertainty, then it doesn't work better because there is nothing, like it shouldn't work better, right? Because the motivation is just for uncertainty. Otherwise, it works better by a little bit, but in all tasks consistently. I think this is Hollywood too. If it especially works much better if the number of dimensions is smaller, because in a way, Euclidean spaces, like if you give it like enough dimensions, they can approximate everything. So if you give like, I don't know, thousands of dimensions, they will get as good as hyperbolic, but they don't have the right structure for it. So if you constrain a little bit the space and giving it less dimensions, that's when hyperbolic spaces work even much better. But in general, they consistently work better for these tasks.
All right, thanks.
Thank you.
So let's thank the speaker again. So our next speaker will be Jordi Pons from Dolby Labs, and he will present a paper from ICASSP that is Upsampling artifacts in neural audio synthesis.
Okay, that was an audio check. Cool. Not just in case, you know, the volume is more or less right. So, okay, I'm Jordi Pons, and I'll be presenting work that I did with Santi, Julio, Joan, Dani, and Davide, that basically are other researchers working here in Barcelona in kind of Dolby office. If you want to know more about our work, here we have this project website where you actually you have code, examples, and also kind of videos, for example, that explain a little bit more the concepts. We'll be talking about neural audio synthesis. So this means that we'll be synthesizing audio with neural networks, and we'll be focusing on a specific problem that is called upsampling artifacts, and now we'll see that. In order to start you kind of developing intuitions about which kind of problems we'll be discussing, let's start with this computer vision example. For example, imagine we want to build a generative model for images. Maybe we want to use transposed convolutions to upsample the latents. And if we use transposed convolutions, these uneven overlaps that we see actually in this video, these can introduce checkerboard artifacts. Okay, this is a common upsampling artifact that maybe or hopefully you are familiar from the computer vision field. But we'll be discussing those from the kind of audio perspective, okay? So now instead of having this 2D signal, instead we have this 1D signal, the audio, and when we upsample with transposed convolutions, for example, we can have these uneven overlaps that can generate periodicities. And these periodicities actually, you know, similar to these checkerboard artifacts, actually they introduce some artifacts that, as you will hear now, they are tonal artifacts. So be careful now with the volume because this is an artifact, so it's not very, you know. Okay, so this is the kind of artifacts you'll get, these tonal artifacts. Okay, so as you could hear, these are not very perceptually very pleasant, so that's why actually we wanted to look onto that to see if actually we could do something on here, understand it better, etc., etc. So basically, another thing I want to show here in this slide is how this tonal artifact looks in the spectral domain. So here on the right, we have kind of the spectrogram visualization where we have the depiction of this tonal artifact in the time frequency plane. So basically, it looks like these horizontal lines that are kind of additive periodic noise that appears there, okay? So that's a little bit the kind of artifacts we'll be discussing. Basically, we've seen the tonal artifacts. Now, we'll see other kinds of artifacts, like filtering artifacts, and we'll also see that the spectral replicas, they can also introduce additional artifacts. So let's start with the tonal artifacts. We've seen already those for transposed convolutions, but for example, subpixel convolutions, which is another kind of upsampler, can also introduce these tonal artifacts. So for example, to build an intuition around that, here you have like a subpixel convolution example, where these actually upsample across the channel axis. So imagine you have these kind of 2 feature maps. You want to upsample these by 2. As you can see here, it's twice long. Now what you do is you upsample across the channel axis. So you see here you have 4 feature maps that now you reshape. You interleave those, and as a result of this interleaving, actually you have this periodicity. So here you see these kind of changes in color, right? So basically, this is again the origin of these tonal artifacts that appear when upsampling. So this is one kind of artifact, tonal artifacts that can appear with transposed and subpixel convolutions. And this was already known, right? We know this from the computer vision literature. They are known as checkerboard artifacts, but now when we look at those from, you know, the audio perspective, from 1D signals, they sound like, as we could hear before, as tonal artifacts, okay? Now let's look at filtering artifacts. And to start, let's see how they look like in the spectral domain, in the time frequency plane. So you see that now we don't have this additive noise. Instead, there's some attenuation of some bands. It's kind of subtractive noise, if you wish. So you see here, there are some bands that are attenuated, and this is how actually filtering artifacts would look like. They will attenuate some bands, okay? And let's see now, again, a quick intuition of why these actually appear. And one common upsampler that introduces this kind of artifacts is interpolation-based upsamplers. Okay, so for example, here the idea is that we first interpolate with, for example, nearest neighbor or linear interpolation. And then, since this is fixed and unlearnable, we often introduce afterwards a learnable, for example, convolutional neural network, because that's the whole game in deep learning, right? To learn these transformations from data. So precisely the fact that we have this part, which is the interpolation, which is not learnable, this actually has its own frequency response, right? So you see nearest neighbor behaves one way, so it has its own frequency response. Or linear interpolation behaves its own way, it has its own frequency response. And these things actually, this frequency response is kept fixed, and you cannot change that throughout training, right? So this actually frequency response that remains there is actually the one that causes these filtering artifacts, okay? So that's a quick intuition, okay? So basically, the frequency response that relates to this interpolation actually is the one that introduces these filtering artifacts. And for example, the same idea actually translates when we use, for example, wavelet-based upsamplers. Here, again, we have some filters that we have to define, that define the wavelet transform or upsampling kind of transform. And basically, this will also remain fixed and also can introduce filtering artifacts, okay? So that's to show another kind of upsampler that can introduce this kind of filtering artifacts. Basically, we describe this kind of artifact that is actually relevant, as you could see, for audio. Maybe for image is not that much important, but actually we found this to be actually important for audio. And now the other kind of thing we discuss in our paper is spectral replicas. And as we'll see now, by means of an example, these actually can introduce additional upsampling artifacts. So I will go a little bit hardcore here with signal processing, but don't worry. So just some intuitions, okay? So imagine, I will go through this example of a signal offset. Imagine you have a signal like this triangle that looks like in the frequency domain like a triangle, and you add an offset to it. An offset is basically a DC. It's a constant that basically has some frequency 0 with some energy, right? If you add a DC or a constant to a signal. So basically, an energy component with 0 at frequency 0 looks like a delta around frequency 0. So that's why we have this kind of delta around 0. This is to express the signal offset, okay? Now, we'll talk about the spectral replicas. So spectral replicas appear in signal processing when we sample or discretize a signal, yes? So we sample a signal, we discretize it, and basically there's some uncertainty that we introduce. In order to express this uncertainty in our analysis in the frequency domain, basically we express this in terms of spectral replicas, okay? So basically you see, you sample a signal and now these spectral replicas appear, and note that when we perform upsampling, basically we are performing bandwidth extension. So now, these different deltas that appear here as spectral replicas, they can appear in band. And what are two deltas in the frequency domain? They are a cosine or a sine, depending on the phase. And what is a sine or a cosine? It's basically the mathematical expression of the tonal artifact that we have just discussed before. So that's the thing. So a very simple thing as signal offsets, actually, they can, each spectral replicas can appear in band and be an additional source of tonal artifacts in this case, okay? Well, anyway, long story short, these are the kind of, origins of upsampling artifacts that can appear. But now the question is, well, how this actually, translates into practice. And in order to have this discussion, let's quickly go through this table. And for simplicity, let's divide these different kind of upsampling kind of layers into the ones that can introduce tonal artifacts and to the ones that can introduce filtering artifacts. And if we look now at the kind of the results, the objective metrics results, for example, SDR, we see that the ones that can introduce tonal artifacts are the ones getting the best results. However, and that's where the things are interesting, when we look at the subjective metrics like mean opinion score that we kind of perform a perceptual study with people, we ask them, and actually people seem to prefer the nearest neighbor kind of interpolation. Well, our hypothesis is that actually the filtering artifacts that don't sound like as crazy as you could hear before, like tonal artifacts, they are perceptually preferable than tonal artifacts, okay? In order to try to keep, explaining this intuition, let me play you an example now with a model that is fully trained, not like before that was just an artifact itself, but now after training, in order to try to see which kind of artifact do you prefer. So let's play here a song, and the task of this model was actually to extract the vocals, okay? And then we'll listen to the separated vocals of this song. Okay, so now basically here you see the bass and the percussion here, that now after, the separation, it's fairly removed. However, look at these kind of high frequency lines all over here that are basically the reminiscence of these kind of tonal artifacts that we were listening before. And now you listen these kind of high frequency noises over there. Oops. Okay, and now you see with nearest neighbor that we don't have these horizontal lines, but instead we have these horizontal valleys. That's again, we can measure these filtering artifacts that we were mentioning before, or kind of describing those from the theoretical perspective. And these are basically here, you see that some attenuation around these bands, and now the question is, well, we don't hear these high frequency noises, and I think this is perceptually preferable. Okay, that's basically it. So we've seen kind of which can be the origins of these kind of upsampling artifacts, tonal artifacts, filtering artifacts. Also, we've seen the role of spectral replicas here. And we've seen also with our kind of perceptual study that filtering artifacts are perceptually preferable than tonal artifacts. Thank you very much.
Are there any questions for the speaker? If not, I can start. So it's very interesting because in image enhancement with computer vision techniques, there is what is called the perception distortion trade-off. So it means that either you minimize a distortion error that is based on minimizing at pixel level, or you are minimizing something that is more global perception of the image. And what it's seen in computer vision is that you cannot minimize both at the same time. So do you believe this is similar to what you are showing here, that you will not be able to minimize both the objective metrics and the mean opinion scores, or you believe there will be some method able to minimize both?
Okay, yeah. So that kind of touches into the evaluation part of it. So minor differences in SDR, for example, I think it's very hard to track like 1% or 0.1 better SDR. This is like state of the art. So many people do kind of like that. However, I have to say that while this might not be enough to say this system is better or not, because they might be actually comparable, when there's 1 dB of difference in terms of SDR, I can tell you this is perceptually preferable. So I would say, yeah, they're fairly correlated when you actually have to distinguish between kind of models that perform enough differently, or the other one is much better than the other one. These kind of objective metrics actually work well for that. Yeah, obviously always having a perceptual test, I think is better, but for kind of separating like the good and the bad model, like when there's big differences, yeah, it works. Yeah.
Any other question for the speaker? If not, let's thank the speaker again. And now the next talk, and actually the last talk of this session, will be done by Santiago Pascual, also from Dolby Labs, and he will present a paper from WASPA 2021 that is called Adversarial Autoencoding for Packet Loss Concealment.
Thank you. So, as it's been very well presented, I'll be presenting this work together, co-authored with Joan and Jordi, about how to repair the voice that may be lost in voice-over IP communication, which is quite famous these days. So I'll first introduce what packet loss concealment is, this reparation tool, and what generative adversarial networks are, and the issue we had with them, so that we prescinded from the generative part of GANs. Then I'll talk about the details of our proposal, PLI for short, the experimental setup, results, conclusions, and so on. So first of all, in voice over IP communication, which is basically a real-time telephone call through the internet, we have packets with voice that can get severely delayed or lost. And there is a component in our receiver devices called the jitter buffer, which is the one sorting the packets, absorbing the delays from the network, and in case of any loss, as in the picture here, we basically, I'm not sure I can point out very well, we would basically call something called the PLC, the packet loss concealment algorithm, so that it fills in those blanks. This can be done with pure zero filling, which would be a discontinuity that's quite noticeable and not very convenient, or with simple classic techniques like repeating the preceding frames, which works up to some extent. Then it sounds robotic, monotonous.
You may notice that many times through internet calls, or interpolations, or more sophisticated, the use of some learnable model, which is why we're here today. So the application of deep learning on going from past to future, which is quite a complex task because there's a lot of uncertainty on what is being said and who's saying it. So let's continue the stream of voice into the future with a real-time model, which is restricted computationally. Now, the thing is, we began thinking on the novelty of applying GANs, generative adversarial networks, into this work, because GANs are basically generative model, which stands for imagine a potential future given a certain past. In this case, in the lower left, in the bottom left figure, you see that there's this deterministic conditioning injected to something called the generator network. This is basically a summary of the past information before a gap. And this generator has to predict what comes next. Typically with GANs, the generator component takes some conditioning information, if possible, and a random vector, the Z, which is a random sample coming typically from a Gaussian distribution. And this is done to sample from a distribution Q of X in the output of G. After projecting the random vector, you get a sample of Q of X in the end, which is imitating the real distribution of samples P of X. Now, the thing is, if we do this with PLC, with something where we are predicting the uncertain future that evolves rapidly, this random component can drive too much importance in the prediction. So speaker identity, contents, prosody can fluctuate very rapidly, very quickly, if the gap extends too long. So basically, we dropped the random component of the generator, disallowing the model to be generative. This is not generative anymore, but instead an adversarial network. Why do you keep the adversarial component? Because of the perceptual enhancement that it offers. An adversarial model, in this situation, it gives us a one-to-one mapping, one past summary to one potential future, but with the addition of better performance in terms of quality than a simple regression. Now, our proposal is built upon an autoencoder for efficiency reasons. And in our case, it's a causal autoencoder because we are only allowed to look at the past to predict the present. And because we're working in a real-time scenario. Now, importantly, this model, as an autoencoder that it is non-autoregressive, and this is part of the novelty of what we proposed. So we're predicting T samples of a gap in parallel. So in this figure, on the right side, you see that for an input waveform with a piece of lost signal on the red square, we also indicate with a binary flag to the model, you have this signal, whether it has or not a loss, because that is a silence for it, that zeros in the waveform. And we flag with 1, let's predict something here that's missing. And in the output, we can see the orange piece of a waveform, which is what the model will deliver in parallel, in one inference shot. Now, after this is done, after this prediction, we take the preceding and the posterior packets for before and after the loss, and we make some linear cross-fading through cross-correlation, typical signal processing cross-correlation. Now, this model is ambitious in terms of trying to guess which are the codec conditions in the input, no explicit signaling, so it should generalize through codec conditions and bit rates for the voice over IP, different kinds of potential scenarios. And also, it's asymmetric, because we figured that if you make an encoder work in the spectral domain and the decoder work in the waveform domain is done like this for perceptual reasons, and let's try to directly predict and get the best quality at the waveform level already, but without any additional decoding process after the network. But the encoding is done in the spectral domain for shallower architectures being able to see enough receptive field of the past to take the prediction of what comes next. So it's faster and shallower thanks to this asymmetric architecture. Now, to experiment with this model, we wanted to compare against quite simplistic baselines like the input itself. So the input signal is zero field in this case, if you notice, is the zero field PLC itself, silence insertion. Then we wanted to compare against two classic baselines, one that does energy decay after 40 milliseconds in a classic voice codec, and the other one is a WebRTC's PLC, openly available, which is NetEQ, and does also some form of short-term packet replication. And then a deep neural network spectral-based model, which is the very first PLC DNN model proposed back in 2015, more or less, and the WaveRNN alternative, which is the closest competitor we have in this work, which is an actual generative model, autoregressive, at the waveform domain for fairness of comparison against an actual generative model. But this WaveRNN, which is inspired by the WaveNet from Google from 1 year ago, is our own interpretation of how to build the WaveRNN the closest possible to WaveNet. We took this neural vocoder that's openly available and converted it into a PLC by making a spectral encoder of the past. Instead of going current spectrum to current waveform, we go past spectrum to future waveform. So we made our own spectral encoder with some cross-validation to know that the model really works well, and it's stable and predicting things that don't go to hell. And I mean don't go to hell because, and here's why we've withdrawn the generative capacity of our model. So this is a generative model, and this is sampling. And in the case of an autoregressive model, as it is a softmax sampling in the output, you have a temperature factor. And this temperature factor allows you to make the distribution more peaky or broader. And this means more or less stochastic, so more certain where you go, stay monotonous, or go a bit wild and explore new paths into the future. So if you have a higher temperature than the one needed, and this is the same reason as why we've thrown the Z in the GAN, the model can go wild in changing contents, changing amplitudes, changing tones, changing the speaker itself. So we really had to tune this temperature factor so that it was properly not going wild, as I was saying, and with some qualitative listenings and some objective metric designs that we did. Now, we can hear to some example reconstructions of what this sounds qualitatively for not very long packet losses in this case.
Ask her to bring.
Can we lower the volume a bit, please? Oops. It's quite tough to see.
Ask her to bring these things with her from the store.
Okay. Not very noticeable, the loss, actually.
Ask her to bring these things with her from the store.
Let me try with the second one.
6 scoops of fresh milk, please. 5 thick slabs of blue cheese and maybe a snack for her brother-in-law.
Okay, the reconstruction for this.
6 spoons of fresh milk, please. 5 thick slabs of blue cheese and maybe a snack for her brother-in-law.
A bit hard to tell with the speakers, but yeah. Anyway, so now the distortion results, what we evaluated were typical speech processing, speech synthesis objective metrics, first of all, to evaluate more or less the content and identity matching, and through different gap loss lengths. And basically the plot on the top right side is showing the trend per model on the Mel capsule distortion, which is correlated to good identity matching and good content matching, as I was saying. Ply, our model, both for codec inputs, so with lower bitrate, or PCM data, which is the Ply itself, the plain Ply, both follow a similar trend of having the lower distortion across different gap lengths. Whereas we can see that classic models, or the DNN model, the spectral one, which is autoregressive and tends to lose energy quickly through time, all of those converge quickly towards the silence upper bound. And this is normal because they are losing energy, so they tend to be silenced in the end. After a few packets have been lost, the gap extends too much, there's no energy to proceed farther. What's happening with the WaveRNN that goes beyond the silence? It's making up things that go with a higher distortion than just not doing anything. This is why it diverges far beyond the silence. So the potential issues of a generative model is it will make things up. You have to control how this works. We don't have a generative model for this design so far, but if we proceed further in this work with generative component again, we have to really regularize it and control how it behaves. Similar thing with the pitch distortion, which means better prosody matching on average. Ply is behaving better through different gap lengths. And we also took SESCA, which is a model that was developed internally and published in the last ICASSP, where the model is trained to take a waveform and evaluate more or less the regression well, actually is trained to evaluate the regression of what a human would think about the signal. So we can see that both Ply and WaveRNN, which are the models trained upon waveform with the latest techniques, the more recent ones that typically give the best quality in terms of speech synthesis, are the ones with best Seska similarity towards the ground truth signals. So they decay the slowest ones with respect to all the other classical models that typically introduce more distortions or do not fill the full gaps all the time. And here is where a tricky result comes in, which is in the intelligibility results. Now, we took, finally, this last dimension, which is evaluating, after the reconstruction, how well automatic speech recognition can detect what is being said in the signal, because in the end, one of the main issues why we apply PLC is to enhance the intelligibility. So we can see that through different gap lengths for 20, 40, 60, and 120 milliseconds, we have different results per model. And note that in the title of the table, the character error rate for the lossless signal is 11.4% with this pre-trained ASR that we took, openly available. We evaluated on clean data. Ply is above this performance at the 20 milliseconds, so destroying packets of 20 milliseconds randomly in this test set and recovering with Ply gave slightly better results than the clean signal itself, surprisingly. We have some fun hypotheses in the paper, but as soon as we go a bit harsher in the loss, then this becomes worse again. In any case, Ply sustained better in terms of intelligibility recovery than the other models, again. And note that WaveRNN is the one diverging the quickest, because, as I was saying at the beginning, the generative model is just making things up so fast that it's just quickly diverging. Here we see this effect again. So as a conclusion, we propose Ply, the first adversarial autoencoder for PLC. The generative strategy, importantly, is discussed, and the use of non-generative learning for this situation is motivated. And Ply consumes a signal that is zero field in the lossy section, learns to reconstruct via autoencoder, which makes it very suitable for real-time processing due to its one-step inference, thanks to the autoencoding strategy. And yeah, it outperforms the considered baselines with these objective metrics at least. Thank you.
Is there any question for the speaker? We have a question here, please.
In the case of the GAN, how were you injecting the Z noise?
Sorry, can you repeat?
Yeah, you said that the generative, the GAN model,
yeah,
you were injecting a Z noise along the conditioning.
Yeah.
So how were you injecting that? Like a bit more in detail.
How did we test that?
Yeah, how was the injection of
the injection of Z?
Of the Z. Yeah.
Oh, so we tried several things, several combinations with the deterministic conditioning, summing up, concatenations, some dropouts on the Z, so reducing the dimensionality of Z or changing distribution, not Gaussian, but choosing, I don't remember, many trials. The best thing was to drop it, basically, so that in the predictions we didn't hear huge, we could really notice a lot of content and speaker variability depending on how you sampled Z. And basically, many concatenations or combination strategies, all the same, concluded in the same direction, so dropping it was the best so far, which doesn't mean it won't work, but at least for a first approach, it worked. Control it by reducing stochasticity this way. But yeah, we tried many strategies. Very good question.
There is another question there. It's coming the mic.
Hi, thank you very much for your presentation. My question is, in the final adversarial network, how many time samples do you consider to generate and fill the gaps? And if you try to with different, with less or more time samples? Thanks.
So if I understand correctly, you're asking about the gap length. So how many samples are predicted?
How many are they for the model? How many time sample is the input for the model, or if it is the
So it is the full lossy chunk, the full of them. So each packet is 20 milliseconds in this configuration long. It can be 10 packets, although performance will degrade anyway if it goes too long. And too long means 80 milliseconds onwards, to give you a sense of a number. But yeah, we insert the full chunk, and it is trained with a myriad of packet loss lengths. So the model has to learn to reconstruct as a masked autoencoder would do, from gap signals to fully reconstructed signals. Yeah. Does that answer your question?
Yes,
okay.
totally. Thank you.
Let's send the speaker again.
Thank you.
This concludes the session. I will now give the mic to Xavier, but let's give a round of applause to all the speakers in the session also, please.
Okay, so thanks again. Super perfect timing. It's just 4 p.m. Thanks to all speakers and chair. Now it's time for the coffee break. When you leave, you go to the right, to the garden. Also for the posters, make sure to interact with all the presenters. And also for the mentorship session. And I would like to introduce Miriam Bellier, who will tell you how it's going to work.
Yeah, thanks, Xavi. So those of you who are participating in the mentorship session of this afternoon, please go to the garden area where the posters are, to the leftmost part. So there's some covered area, and you will see that there are some tables with a paper that says mentorship. So that's where we are. And please, both the mentees and the mentors go to talk to me and to Agatha. So we will tell you which are the mentors and the mentees that correspond to you. And yeah, that's all. Thank you.
So see you back at 5 and get your jacket because it got a bit colder outside, okay?
la teva presentació i al final posaré em crides i fem això.
I també comentar el tema dels hirings que volem fer a Europa. Els 10.000 persones, allò que van dir...
Ho pots dir, sí, ho pots dir. És el tema, en termes molt generals.
Sí, és que no
sabem res.
Efectivament.
No sabem res.
No seran 10.000 investigadors, però bueno, hi ha la voluntat de...
Hi ha la voluntat de fer això.
Vol dir que deu estar atents.
I la Sara farà el seu discurs molt estàndard, suposo, parlant sobretot d'Europa. Voldria que parli també dels Estats Units i de coses, d'enginyers també. El vol centrar sobretot a internship de recerca i Jordi.
S'havia connectat, crec, la Saira es diu, potser?
Saira.
S'ha connectat i s'ha desconnectat. Estàs parlant amb ella, tu? Perquè ha entrat i ha sortit.
D'acord, li dic de connectar, de seguida.
Sí, perquè just ara, i l'he deixat entrar, llavors potser és just al moment que l'he deixat entrar, ella s'ha cansat d'intentar entrar. Val, ara estan trucant a la persona de Londres perquè es connecti.
Normalment està esperant que el tinc. Hey, Sarah. Yes, you can connect to the Google Meet right now. Okay? Bye.
Sí. Bueno, jo també la tinc aquí. Jo crec que té accés, però si no té accés m'ho demanarà aquí. És que abans s'ha connectat, A les 5 comença en Joan Bruna. Ara, i ara hi ha la Saira. Ok.
Hi.
Okay, hi Saira, I'm the chair of the Symposium, and I think that Pierre-Louis is just over there. Okay, so has connectat. No, Saira, are you there? Vale, sí.
Can you hear me?
Yes, parla tu amb ella, des d'aquí. Bueno, tu parla.
Hi, Sarah. Can you read it correctly?
Perfect. I just had the internet drop there, but I don't know if it was from my side or your side, but I think it's all fine now.
Wow.
Can you see me clearly? Can you hear me clearly?
Hi ha molt d'eco.
Eco, vale. Et porto un tècnic. Diu que hi ha eco. No és tècnic? No.
There is some echo here.
El tècnic et sent. Diu que hi ha eco.
Hi ha eco.
So, ask her to... Saira, just keep speaking. Because we need to...
Yeah? All right, guys. I'm just going to try share my screen with you guys. Your screen. Let me know how it looks. Can you guys hear me clearly right now? I might just delete the video. Pierre-Louis?
Yeah.
Make sure we're even
Can you try? So I will ask you to skip the slides. Slide one, next slide, because we can do that here. And can you try the video, starting the video, just to check?
This one, yeah.
We always ask, where is the future?
Sorry, there we go.
Yeah.
We always ask, where is the future going to take us? But the real question is, where are we going to take the future?
There are no closed doors, no walls.
Holy mackerel, this is unbelievable.
You may have brain surgeons in Edinburgh operating on patients in New Zealand.
You'll send emotions, feelings, memories.
Imagine a world where we are represented the way we want to be.
No, in future, it just feels like long distance won't be so distant. There's a big future. Where do you want to go?
And we're just getting started.
Appreciate the past, utilize the present, but don't be afraid to create the future.
We always.
So Pierre-Louis, you want me to delete this?
Sarah, the experience is not that good because of the network lagging. Either we skip the video, either we find an alternate option to play the video from here.
Let's delete it.
Actually, the video is here. So just the video is public, and you have it in the website, in our website, actually. The video, not the rest, but the video is public because it's in YouTube.
So shall we delete it from our presentation? I think it might be the best if it's poor quality. If the streaming poor quality, let's delete it then.
Okay, I'm trying to just play only the video from another computer that we have over here. You see, Pierre-Louis. So you see, if you want only to play the video, we can play it from here, okay, and then switch to what's her name? Sarah. Sorry, to Sarah later. So I can put in this screen when you tell me the video, and then switch to the Meet when you tell us.
Okay. Who switch?
The people over there, they can switch between this computer or the Google Meet. That's something that they do all the time.
I should ask to switch.
Yeah.
Or you?
I will be there, so if you tell me more or less when is that, we can just say, can you play the video, and then we can play it as you wish.
So Sarah, we'll be starting with the first slide. Then when we need to switch to the video, they will play the video from here. Okay, then we'll switch to our deck and you online.
Perfect. So once the video is done, they will pass over to you. Are you happy with the agenda? To talk through that. Then you'll pass it over to Christian. And then Christian passes it over to me.
Yes.
Yeah. And then I do these slides, and then I finish it off with Facebook Quiz, and then I pass it back to you, Pierre-Louis.
Yes, okay, that's correct.
Perfect. In terms of just the video, Pierre-Louis, it might make sense for you guys to just play that video, the first thing you guys do at 6 p.m. So when everyone's sitting and just getting ready, you can just play that video at 6 p.m. And then once the video is complete, they can put your slides up. So it's a very smooth transition in that sense.
Okay. Yeah, so I think that what she says is that at 6 p.m. we just play the video, and then we go to Sarah and the Meet, and then she takes it from there. Is that what you meant, Sarah?
Yeah, so at 6 p.m., you can play the video. Everyone should be seated by then.
Yeah.
And then there will be something warm for them to kind of start watching. And then once the video is finished, I will present my screen, and then Pierre-Louis can go ahead and introduce himself.
Yeah, that's great. Yeah, that's better. Let's rehearse, okay, this, because I think that probably you can see, let's see, the video that we have in our computer, but I'll try to speak to the technicians, so now I'll speak to them. Val. En aquest ordinador tenim un vídeo, el que farem és quan comenci l'acte, tirem el vídeo des d'aquest ordinador i després sí que passem al Meet. Sí? Podem fer la prova ara? Imaginem-nos que comencem. Vale, quan tirem el vídeo, l'àudio també s'hauria de sentir del vídeo. El poso? Vale, perfecte. Hauríem de sentir l'àudio, no? No podem sentir l'àudio? Està a l'altra banda, algú a l'altra banda. S'hauria de sentir l'àudio del vídeo que estem veient. Posat? Vale, sí. Bueno, no sé, Sí? No tinc molt clar. Espera, que l'he parat, cara. Vale. Està sonant aquí internament el vídeo en el portàtil. No sona per... No sé si tenim una sortida d'àudio a algun lloc. O li podem tirar des d'allà, el vídeo. Aquest vídeo puc tirar des d'allà. Us el puc tirar des d'una màquina vostra, també. No cal que sigui aquest portàtil. És més fàcil, no? Si ho tirem des d'una màquina vostra aquí dalt. Creus que sí, oi? Doncs pujo aquí dalt i te'l preparo. M'has sentit? Però si és només el vídeo, no hi ha un altre ordinador allà, que així ho controlem nosaltres.
Sí, com vulgueu.
Sí, és més fàcil, no? Així ell es preocupa d'aquest ordinador i ja està.
Però s'hauria de sentir,
Bueno, jo pujo a posar-lo en un altre ordinador allà.
Si ho has de posar en un PC...
Jo dic, que en lloc de fer-ho aquest portàtil, allà no hi ha cap ordinador que puguem.
El podem provar. Prova de baixar-te'l allà. Ara pujo. A veure... Vale.
Núria, a l'ordinador d'aquí, el d'aquí dalt, per on m'ha d'arribar el so?
Quin està utilitzant?
El que teníem a darrere a l'esquena.
Tricaster.
Tricaster? Doncs tampoc m'arriba.
Tampoc. Vale, si no que el posi el PC2.
PC2?
El del Meet.
Vale.
Perquè si hem de fer un canvi... Espera, que pujo.
Repeteix, que no t'he sentit.
Ha sigut, tio.
is the future going to take us? But the real question is, where are we going to take the future?
There are no closed doors, no walls.
Holy mackerels, this is unbelievable.
We may have brain surgeons in Edinburgh operating on patients in New Zealand.
You'll send emotions, feelings, memories. Imagine a world where we are represented the way we want to be.
You know, in the future, it just feels like long distance won't be so distant.
That's a big frontier. Where do you want to go?
And we're just getting started.
Appreciate the past, utilize the present, but don't be afraid to create the future.
Hey, Sarah. So this is Chihiro, I'm the organizer. We're gonna do what you suggested. So we can play from our own computers the video in, like, say, full resolution, and then we will switch to Google Meet where you are, and then you take control of the slides. And I think she will see Pierre-Louis, right? I think. So you will also see. Well, I mean, she will see the person who's speaking here. Okay, so she will see. So Sarah, you will see the person who's speaking, and I think we take it from there. Is that right?
Thank you so much. So after the video is finished, it is my cue to upload the slides. I mean, share the slides, or can I do that
you
when
just.
the?
I mean, you just the way you have it now. I mean, the point is that now in this call there's going to be a talk by Joan Bruna. So now just remove the slides. But when that talk is over, so that's at our 6 p.m. I guess it's 5 for you. You can maybe a bit earlier. Just join in, and you can see what's happening. But we are in really good time, so it's going to be really at 5. Then you just share the screen and so on. But it's looking good the way it's doing now. Okay?
Perfect. Thank you so much for your help and your support, and I'm looking forward to the event. So thank you so much.
Yeah, thanks to you. Bye. See you in an hour or so.
Bye.
Joan. Hola, benvingut.
Ah?
Bé, bé.
Però que aquesta música és la teva o...?
Sí, és nostra, nostra. És maca.
Ah,
és molt bona. Escolta, Joan, me'n vaig a baix, a la presentació m'hauràs per una altra banda.
Ok, perfecte.
Si vols compartir pantalla...
Vale, vaig a provar de compartir pantalla.
Molt bé. Em podeu posar en Joan a la pantalla? Que em senti... Joan, em sents bé?
Et sento bé, sí, et sento bé. Tu també em sents a mi?
Et sentim bé? Sí, sí. Crec que està tot controlat. Doncs res, 3 minuts i començarem, d'acord?
Ok.
Moltes gràcies i disculpa aquest canvi d'adreça últim moment.
Cap problema.
Okay, so it's 5 p.m., so it's time to start the first of our keynote. So if you can put Joan Bruna on screen. Yeah, can you put Joan over there? Hi, Joan, can you hear me well?
I can, yeah.
Great, so we can hear you, so I think we are good to go. So welcome, everybody, to the first of our keynote talks by Joan Sarrà, called Geometric Deep Learning Prospects and Challenges. Joan Bruna is an associate professor at the Curran Institute of New York University in NYU, and he is one of the 4 co-authors of the protobook Geometric Deep Learning. He obtained the bachelor and master degrees here at UBC in both mathematics and telecommunications engineering. So we have tried to have Joan in the Deep Learning Barcelona Symposium since the first edition in 2018. It's a very huge, great honor to have him today with us. So Joan, thanks a lot for being remotely with us today, and the screen is yours.
Okay, thanks. Thank you, Xavi. Gracias, Xavi, personally for the invitation and also for all the work that you have done, not just for this symposium, but over the years, trying to really push the deep learning and put Barcelona in the map. So thank you very much for that. Okay, so I'm going to talk to you today about this general set of tools, or like something that is, one could also say that is like an emerging subfield of deep learning, where the goal is really to try to extract or like to combine the kind of general principles of deep learning with something about the physical world. And so really like the starting point is the same as you would expect. So basically we are today almost like 10-year anniversary of this, let's say, experimental revolution, like a breakthrough that really put deep learning into the minds of like serious people, right? Everyone. And it started as an affair of computer vision, as you might remember from this like ImageNet competition. But over the years, we have seen deep learning start to actually bring more and more attention beyond computer vision, and now it's essentially everywhere in scientific in the computational sciences, in biology, in chemistry, in physics, everywhere you could imagine. And so, in a sense, like some kind of analysis, or like let's say what's going on, what's happening, and why this is happening. Really, what we see is that these models really have the ability to capture information, extract information from all these data. Like something that these data all have in common is that they're all living in a high-dimensional space, very high-dimensional space. At the same time, it's a structured high-dimensional space, as we are going to see today in the talk. But really, like the essence of deep learning is this ability to what we call representation learning, to extract useful features out of the data in a way that is automatic, right? Like the data is going to extract these features for us. And the procedure, like the algorithm to do that, is in a sense something that you could argue that is quite naive, right? It's just try to start from arbitrary features and adjust these features with some first-order method, for example, gradients. And so, somehow the state of affairs is not satisfactory, right? I mean, the current methods are incredibly hungry, right? Hungry for data, hungry for compute, hungry for parameters. And as a result, maybe the situation right now is not ideal because if you want to really make a big impact in some of these domains that I described, like be it computational physics, chemistry, games, like a data set, you need to be essentially Google, right? To be able to train these models and to handle the infrastructure behind it. The other problem is that we are now in a situation where every problem, every domain, maybe let's say language or vision or speech or chemistry, seems to have developed its own set of like recipes. And every recipe you can think that it's like an animal, right, in a zoo. And so at the beginning, people were, every animal was a different world, like a different science object, right? But at some point, we really want to understand what do these things have in common, right? Is there some sort of like a guiding principle that we can use to really put together all these architectures and understand all the choices that the different practitioners have made for the different domains in some kind of like a common mathematical umbrella? And the reason why we want to do that is because we believe that if we understand these principles, we are going to be able to get farther beyond than if we don't. And so today, I'm going to, of course, give you like a very high-level overview of this direction of geometric deep learning, trying to basically bring this kind of unification together. And first, we are going to spend a little bit of time describing where we are in terms of math, right? If we really want to understand, what are the things that are, what are the mathematical theories in which current high-dimensional learning is sitting, we are going to see that we really need to go beyond what is currently there. And so then we are going to describe this set of tools, algorithms that we call geometric deep learning. And then I'm going to close the talk with some applications on a direction that I personally believe it's kind of the future of, people here who are listening to us and want to, do a career in deep learning. This is really like a set of applications where I think it's incredibly rich and rewarding. So I'm hoping to give a little bit of an overview of some of these applications that we call this scientific machine learning. All right. So if we start from, like they say, like the simplest of the simplest learning setups, which is supervised learning, right? It's like nothing fancy, nothing like self-supervised learning or reinforcement. It's like the basic supervised learning. The way we typically try to understand the success of an algorithm, of a learning algorithm, is basically by trying to evaluate how well, so we have an algorithm that in that case, I just summarized here with just one line, one equation. This is for those of you who are familiar, this is what the famous empirical risk minimization. So basically the idea is that you have an algorithm that can access to some training loss that I call here R hat. And through some algorithm, you can produce a hypothesis, F hat, right? F hat is a hypothesis that you produce. And so we typically evaluate how well this hypothesis does in the real world, in the test data, by comparing it with the best possible function out there, right? That's the kind of a posteriori, what is the best thing that you could do. And so typically to understand like, what's going on, the ability of a hypothesis to generalize, we typically take this error and we break it into different sources of error. And so probably you have seen this kind of decomposition of error before, but there's basically three major sources of error that emerge. One is the approximation error, which is basically capturing the ability of your architecture, of your function class, to express the functions you care about with small complexity, right? So you want to basically try to adjust your architecture to the functions that you want to learn eventually. The other one, the second one, is what we call the statistical error, which is really penalizing us. We are paying a price for optimizing the wrong function, right? So when we train our algorithm, we are not optimizing with respect to the test error. That would be cheating. We are optimizing with respect to the training error. And because these two functions are different, the minimizers are generally going to be different, right? So we need to pay a price on that. And then finally, that's an important source of error, is that we also pay a price by the inability to solve this problem, right? As you might know, as you might suspect, solving this empirical risk minimization when we have to involve very complicated deep neural networks, the optimization problem is generally very complicated, right? There's this like a non-complexity that is hitting us. All right, and so these problems, this error, the bad news is that in fact that we have very little mathematical guarantees to make sure that these errors are going to be small. In particular, as the dimension of the input grows and grows and grows, right? Which is what you should be looking at if you try to understand why, let's say, ImageNet works, right? We have inputs that have, almost like 1 million dimensions. And so when we try to understand how, like we try to plug in classical hypothesis spaces from like classic analysis, mathematical analysis into this picture, we see that things are not so easy. In particular, if you look at for spaces of hypotheses that are very large, basically we try to make very little assumptions about the world, right? We just say that the function that we want to learn is just Lipschitz, which means that if you perturb the input a little bit, the output is going to change a little bit, right? That's reasonable, but that seems pretty weak assumption. So as we all know, this space of functions is far too large, right? So like the approximation error is good, right? Because this hypothesis is correct, but the space is too large. The statistical error is out of the window, right? In the sense, you want to identify a function that is Lipschitz, we need to have basically a number of points that is of the order of basically e to the epsilon to the minus d, right? So the number of training points to preserve a certain error blows up exponentially with the dimension. We can make the hypothesis spaces smaller to maybe control the statistical error, but then we can do that. Of course, math. We go to some classic book from from analysis, from the 20th century. And we have, for example, this ability to say, okay, I'm going to ask not only the function to be smooth, but maybe the derivative of the function to be smooth, right? So I can put as many derivatives as I want. So indeed, if I put as many derivatives in my hypothesis that is like of the order of dimension, then indeed I break the curse of dimensionality, right? There's no, I can identify functions in that space with a number of samples that is no longer exponential in dimension. But what have I lost? I have lost any ability to express interesting functions, right? I'm trying to visualize this thing and put you a little picture here. I don't know if you see the cursor. If I start to put more and more derivative in my hypothesis, I end up just having functions that are incredibly smooth, right? So I can only learn things that are incredibly smooth in the high dimensional space, right? Which is not a good assumption in practice. Over the years, recently, this is Andrew Barron was a kind of a key figure in the neural network research, more like the theoretical research in the 90s. He came up with different spaces that basically supplement or resolve some of the problems of the first kind of Sobolev hypothesis, right? And these are even called like Barron spaces now, or variation spaces. So these are spaces that are really well adapted to shallow neural networks, right? So these are basically the right spaces that where you could learn efficiently with shallow neural networks. And for those of you in the audience who are familiar with the Fourier transform, if you look at the Fourier transform of this function, right? So it's like the Fourier transform taken on the high dimensional space. These are functions whose Fourier transform is really concentrated in this rays, in a small number of rays. So is this something that is useful? Is it something that is valid for us? So we can take a little illustration here. So think about this function where I call this function that is the Hermite crab detector. So it's a function that takes as input an image, maybe of a crab, and outputs whether this image has a crab or not. So this Barron hypothesis, in general, like the Sobolev hypothesis, would basically tell us that if the function, if I can replace the function, the input, by its low frequencies, right? I'm basically making the function depend only on a small number of coordinates, right? So that would indeed break the curse of dimensionality, but unfortunately, many problems in vision, they really require the high frequencies, right? If I blur everything, right, I lose the ability to recognize, right? That's why people wear glasses, right? You need the high frequency information to be able to get information from the world. And in fact, this Barron hypothesis, this idea that I told you that the function has Fourier transform concentrated in a small number of directions, essentially, I'm not going to expand on that here today, but basically what it means is that you can take the function, like that, you can take your image, and you can break it into a small number of patches or regions, and basically the function that you are trying to approximate, you can do it with a small number of interactions, right? So instead of looking at all the possible ways the pixels can interact with each other, I can reduce these interactions to a small set, right? In the case of images, a good approximation would be I take my input image, I break it into a small number of patches, and then I predict the output by just aggregating local detectors, like local decisions, right? That's what is in this formula here. As we know, that's not something that captures all the richness of vision, right? Most of the information that matters here is really in how these patches interact with each other. In other words, there's long-range interactions in many of these vision problems. And these long-range interactions really blow up this norm in that spaces. So basically the point here is that if we really want to capture structure, right, what is the right regularity for the functions that we care about, we really need to look at it in the domain, right? Here the input, I told you that it's an image, but the image is itself a signal over a low dimensional grid, right? So here you are really visualizing a two-dimensional structure, right? That's the two-dimensional grid of pixels. And that's where we need to look for structure. Okay? And so that's what we are going to do here. And what is this geometric function classes that we are talking about? Okay, so this is basically what we are postulating is the target function that we want to learn. Is we know that it's smooth along certain transformations of the input. And we are using the domain, like the two-dimensional grid, to specify these transformations, right? And here, I'm hoping that this video is going to play. You can see that here I'm basically applying, this is a video that I didn't make. It's a very nice video by Philip Scott Johnson that really makes us go through 500 years of painting for female portraits. And as you can see, the transformations are really obtained by applying warping in the two-dimensional grid, right? And so that I have a way to transform the two-dimensional grid, and this transformation lifts into transformation over images, and the function that we care about, in that case, maybe like the identity of the painting or like the style, it's a function that is not going to change too much along these transformations. And this regularity, the key point here is that it's not saying that the function is Lipschitz, or it's not saying that the function is Sobolev, or it's not saying that the function has low Barrow norm, right? That's a completely different notion of regularity. And that's what we want to exploit. And that's what we are exploiting with geometric deep learning. Okay, so let's try to do that, and let's try to see how far we can go. So the first natural way to maybe exploit these geometric function classes is to look for symmetries. Okay, so symmetries are, of course, very connected with this transformation that I described, in the sense that I can apply a transformation in my domain. Okay, I can apply a transformation of my function, and I declare that this transformation is a symmetry of the function if the function doesn't change, right? In this example, let's think that I apply rotations of the two-dimensional grid, right? So if I apply a rotation of the two-dimensional grid, I can apply this rotation to any input, and I can declare that the identity of like the style of the painting does not change, right? So this function would be constant along what we call these orbits of the group. Okay, so these symmetries are nice because I can combine them with each other, and I still get another symmetry, and so they have this very nice algebraic structure, which is called a group structure. And so here's a very simple idea, right? I can start from my learning problem, where I have like a huge hypothesis space of possible functions. I have my target, and I'm promising you that the target is invariant, right? Like the target function f star lives in the space of functions that are invariant with respect to some group. And I know the group, right? The group is known. And so very naturally, you can say, well, why don't we restrict the learning into the green space, right? That's a space of hypotheses that themselves are invariant. That's pretty natural, right? Seems pretty natural, right? Because I'm going to learn over a space where the approximation error is the same as before, because the target is in that space, and the space is smaller. Therefore, it has smaller statistical error, right? So it can only be better. The problem, like the question is, how much better, right? Can we actually break the course of dimensionality just by arguing in terms of symmetries, in terms of invariance? So for this, and this is actually work that we presented recently at Muriel's with Alberto Vietti, who is the main author, and Luca Venturi. So these are both collaborators here at NYU. And so here, to really quantify these gains, we can look, for example, at the Lipschitz class as before. So that was the original hypothesis, just asking the hypothesis was Lipschitz. And now we are going to make the hypothesis much stronger. Right? We are going to assume that the function is not Lipschitz with respect to this metric, but with respect to the metric that looks at the distance between orbits. Right? So in other words, we are combining the Lipschitz assumption with the invariant assumption. All right? Of course, as you can see, this distance here, right, is much weaker than this distance here. Right? So basically, Lipschitz with respect to a weaker metric makes it into a stronger hypothesis. So here's the main result. I'm just basically summarizing it for you, is that if I use this, if I combine basically the classic notions of regularity with invariance, indeed I can do better, and we can quantify how much better we do. And basically the gains in sample complexity, right, like the expected generalization error that you're going to make, is going to be improved. It's basically, essentially, you would replace the number of training points, but the number of training points times the size of the group. Okay, but those who are aware, I mean, who can read, I mean, those who have maybe anticipated, you can see that these gains, right, are inside an exponent that is cursed by dimension. Okay, so in other words, even if my group of invariants is very large, for example, permutation invariant, right, which is like a super large group, and it's used for, you know, processing, let's say, graph structured data. That seems like a very strong assumption. So even if I have something here that is exponential in dimension, it's going to be kind of, these exponential gains are going to be canceled, are going to be kind of killed by a rate, an exponent that is pretty bad, right? That is cursed by dimension. And so the point that I want to make here is that, yeah, invariance can be very helpful, right? You can actually boost your learning guarantees, but in its own, it's not sufficient to explain why it works. Because I still have a problem here. I have a big problem here, right? The exponent is still very bad. Okay, and invariant is not going to be able to change the exponent. Any questions so far? Yeah, by the way, I forgot to say that I'm very happy to get interrupted by questions, or I don't know if Xavi, how you want to moderate that, but anyway, if there's no questions, I'll keep going. All right, so the takeaway here is that really we need to complement the invariance with another prior. And so, of course, we are not by any means the first ones to observe that. In fact, if you look at the many of the talks by very influential people in the field, like Jan LeCun or Yoshua Bengio, they all observed that in fact there's another ingredient, key ingredient, that explains the success of deep learning, at least explains it at some intuitive level, which is this idea of compositionality, right? This idea that we can somehow break an estimation problem, like instead of us trying to estimate the target function that depends on, that lives in a very high dimensional space, we can somehow break this estimation problem into a sequence of smaller estimation problems, right? And so this is what they colloquially call compositionality, right? And Jan goes up to explain that maybe for CNNs, this compositionality is related to some kind of like a increasingly complex spatial structures. But of course, this compositionality is also something that is motivated or like consistent with what we observe from neuroscience, right? Like the brain also has this kind of like hierarchical structure. And so how can we actually, maybe hope to formalize this notion of compositionality that has to be combined with invariance? Well, here's something that physics can help us a lot, because that's the notion of scale, like multi-scale, like the idea that very complicated phenomena, for example, if I want to understand biology, I mean, how life works, of course, I can start at the atomistic level, right? Try to, understand molecular dynamics, like draw equations of motion for molecules. But if I, it's going to be impossible to use this like a formalism all the way to explain, I don't know, why a baby learns how to walk, right? I mean, this, in a sense, we need to really break the problem into different scales, right? So that if we want to make any sort of progress, right? And this idea of trying to understand something very complicated by understanding how it operates at different scales, it's really at the core of many, many physical phenomena, right? I mean, here I'm just illustrating a few of them. Turbulence is another example where we can really understand the physics of this phenomena by understanding what happens at different scales. Percolation is another very nice physical model where, again, there's a notion of criticality that depends on some kind of like a scale operation. Okay. Yeah, by the way, I'm not seeing any chat, so Xavi, if there's anything, you can maybe tell me offline or something. All right. Okay, so how can we combine this idea of multi-scale with the, what we have been saying before, in terms of basically invariance in the context of this geometric deep learning? So really, there's a very natural way to connect them, and we can specify these in the grid, right? By just looking again into problems that involve computer vision, where the group of transformation in that case is given by transformations and this warping that I described before, right? This idea of that you try to deform the domain by applying a smooth deformorphism. And so in the grid, we can first look at basically linear operators that are stable to this transformation, right? So basically linear operators that have the property that when applied this deformorphism, this warping in the domain, the output doesn't change too much. So in fact, it's not hard to see that the only linear operator that has this property is the low-pass filter. It's blurred, right? If I blur the image, I get features that are stable to deformation. And these are the only linear operators that have this property. As we said, this is not sufficient, right? If I want to do recognition, I cannot just keep these low frequencies, so I need something to complement those things. And the key idea here is that instead of looking for linear invariance, we're going to look for linear equivariance, right? So linear operators that instead of being unchanged when I apply the transformation, we are going to look for linear operators that commute, right, with the action of the group. Okay, so in other words, if I look for translations, that would be linear operators that commute with translations. And so here, from maybe your undergrad class on signal processing, you might remember that these are precisely convolutions, right? Convolutions are operators that are linear and commute with translations. But remember that the physical priors that we described are not just, this picture that we saw before. They are not just like rigid translations of the other, right? Like the kind of the group of transformations, like the class of transformations that we care about, are something slightly more general than translations. They are kind of these deformations. And so which of these convolutions are going to be stable to deformations? And that's where the multi-scale phenomena appears again in a way that is pretty clean and pretty natural. And this is really some of the work that that was the beginning of my career, something that I did during my PhD alongside my advisor, Stefan Malan. And so the idea here is that I define this filter bank of wavelets. So what is a wavelet filter bank? It's just a collection of filters where I take some some high pass filter like that is localized in space. Think of it as a kind of a gabor, and then I just create copies where I change the orientation and I change the scale. Right, so I extract information of the image at different scales and orientations. And in fact, like a fundamental property of this filter bank is that this filter bank is essentially commutes with diffeomorphism. Right, so basically the commutation error is of the order of the distortion. Right, so it doesn't blow up. Like the high frequencies here are really kept stable. And that's a key property. Because now we can take this high pass filter, this collection of wavelet filters, we can combine it with our low pass filter, and we can combine it with another operator that in that case is nonlinear, that also has complete stability with respect to deformations, right? These are operators that are pointwise, right? So if I have an operator that looks at an image with pixels and applies some transformation that is pixel-wise, it doesn't matter if then I take the pixels and I move them, right? Because the transformation is only pixel-wise, it completely commutes with this transformation. And so now I have this picture where I have three operators that are all stable to deformations: the low-pass filter A, the bandpass filter W, which is the wavelet filter bank, and this pointwise nonlinearity. And so I can play the game of trying to combine them, right? So basically I have here, So basically what I do is that I can start by just extracting the low-pass filter A. Then I can see, okay, this low-pass filter is losing a lot of information. So I need to complement it with my bandpass filter W, right? That's the next thing. Then I can take this bandpass filter, right? And I can apply, at the output of this bandpass filter, I can apply this element-wise nonlinearity. This is still stable. And then I can extract stable coefficients, right? By applying the low-pass filter. And every time I apply the low-pass filter, I'm throwing information, right? I'm losing information. So every time I apply this low-pass filter, I recover the information that I lost in the next layer by applying another family of wavelet filter banks. And this is really like the multi-scale wavelet scattering that we introduced actually almost 10 years ago. It looks like an eternity. And so the point is that because we are using these kind of operators that are designed to be stable to deformations, if we compose them, right? If we start combining stable operators, we are still stable, right? We can actually completely control how this representation changes when we apply a deformation in them. All right, so this is actually a nice object that is only using this kind of like a first principle approach, but there's some limitations, right? In particular, here this representation cannot model interactions between different wavelet coefficients, right? I mean, every time we apply, we have a feature map, we just take this feature map and decompose it again in wavelets, right? But there's no interaction that we capture between different feature maps. And so this really has an impact in approximation power. Okay, so these wavelet scattering coefficients, they are very useful to, let's say, solve, maybe MNIST and also like some simple classification problems, maybe like CIFAR. But if you want to try to do that in ImageNet, you see that it doesn't work as well as the latest CNNs, right? So the point is that a natural way to take something that has similar mathematical guarantee, like similar mathematical principles, but more general, right? So you introduce a bit more flexibility into the architecture without throwing out stability, is to look at the general interactions between these filter bands, right? So in other words, we have again our family of local filters. So think about instead of having wavelets at different scales and orientations, now I have a different family of oriented filters, let's say local partial derivatives. And so I have this family of operators that are local, that are linear, and they are stable, right, because they are local. And the network is just learning on top of this family of filters, right? It's basically just learning how to combine different stable operators to produce features at the next layer. Okay, so the takeaway here is that we need to think in terms of intrinsic learning, right? We have a family of operators, right? In that case, our partial derivatives, and we are learning linear combinations of these differential operators, right? And because this family is designed to be stable, any linear combination is going to inherit the stability. This decomposition, in fact, extends directly, right? So this operator here that I'm applying this convolution, we can apply it in much more general settings than just the grid, right? Any Lie group, for example, if you want to learn things on the sphere, exactly the same principle applies. Okay, so is this something a bit more general, right? Is there like a general procedure that extends natural distance? And so what do I mean more general? What I mean more general is that we might be interested in using the same principles on data that really has no regular structure like the group, right? For example, you could say I have a molecule, and I can represent the molecule with a graph, right? So every node might be like a different atom, and every edge might encode a different kind of chemical bond. Or I might be able to, to solve problems in computer graphics where my input might be like a mesh, like a manifold more generally. Okay, so these domains, there's no notion of regular brain. But still, we can, as we are going to show next, we can still apply exactly the same ideas. The ideas that kind of underpin this notion of like multi-scale wavelength scattering and in general like this multi-scale CNNs. And so when we take this domain, I'm going to maybe just focus on the case of a graph, and the case of a manifold is following basically the same idea. So when I take a graph, I can embed this graph, right? I can express it in my computer, maybe with an adjacency matrix. So an adjacency matrix is just a way to express the graph. But this embedding is not one-to-one, in the sense that there's many, many different adjacency matrices that represent exactly the same object. In particular, these are the adjacency matrices that are conjugate, right? So if I apply a permutation, the same permutation over the rows and the columns, I'm just getting a different matrix, but this different matrix is exactly representing the same domain. So this naturally gives, induces us to be careful, like to learn a representation that is going to be invariant, the representative, right? I want to have a representation that is well defined, that only depends on the graph, does not depend on the specific symmetric that I choose. And not only that, in these domains, I can also define a notion of a deformation of the domain, right? So I can take two graphs, and I can ask the question, how similar are these two graphs, right? The same way that when I took my image and I apply a deformation, right? There's a notion of two images that are geometrically close, right? If the deformation that goes from one to the other has small norm. So here, it turns out that we can define the same things, both in graphs and manifolds. There's this notion of deformation of the domain. And so what we might ask is, can we build a representation that is intrinsic, in the sense that it doesn't depend on the representative that I choose, and not only that, that is stable to these deformations of the domain? And so the answer is really going back to the kind of the essence of what we saw before. Is that what we saw before is that essentially we used the notion of a low-pass filter and the notion of a high-pass filter. And these are just instances of something much more general that are really something that is everywhere in physics and math, right? Which is this idea of diffusion, right? Like this idea that I can take any domain, for example, like even like a graph or a manifold, and I can apply what we call a diffusion, right? If I have any signal that lives in that domain, there's a notion of like blurring the signal, which is basically running some diffusion process on top of it. And this plays the role of the low-pass filter. And then not only we can apply a diffusion, but in many of these domains, in both in the graph and manifolds, there's an analog of a high-pass filter, which is basically just subtracting the signal from its low frequencies. And this is really like a Laplacian operator. So these two operators are basically, I mean, we could even go as far as saying that these are the foundation of geometry, like understanding that diffusion and Laplacian is essentially what geometry is about. And so with these two things, we can build our network, right? And so here we take, we can consider this family of generators, which are given by these operators that I just described, maybe like a diffusion and a Laplacian, and I can just consider them as what my family of operators, right? And so now I can replace my CNN layer instead of like learning a linear combination of oriented filters, I can learn a linear combination of stable operators. Okay, and this is something that is what we call in this project with Michael, Taco, and Peter, we call this geometric deep learning blueprint, because in a sense it like extends what we do for CNNs, and also gives us a way to think about this model, this architecture, much more generally, right? And it's something that we can apply for graphs, we can apply for manifolds, and we can apply for, as I say, general groups. Okay, and so the key point here is that we learn intrinsic combinations, linear combinations of operators, right, that are linear. Some of these operators are all linear, and basically we kind of, if we understand very well these kind of stable operators that are linear and equivariant, then we can plug them into this pipeline and get like very powerful signal representation. Of course, this is really like a very general blueprint, but it's not completely prescriptive, right? I mean, there's of course you might have the question, how can I choose this family of operators and what are the trade-offs, right? And here we have, there's a very natural trade-off that appears that concerns, the stability versus the approximation power. Okay, and so there's of course, like still a lot of ongoing interesting research that really explores this trade-off. We are not gonna go much deeper in detail today in this talk. Okay, very good. Okay, so like kind of some of these like takeaways that I want to kind of present in this direction really is that this kind of like thinking about the problem in terms of symmetries and in terms of stability to deformations, it really gives us some amount of guiding principle, right, that we can use across many domains, right? And so here's an example of when you look at the different domains and you look at the different symmetry groups, what kind of architectures, right, you end up having. All right, and this is really just a takeaway that is trying to put this in a more table-like thing, right? And so really here, what for example, things that are still open, right, that are still like I would say not very well understood from a mathematical perspective is, for example, how to connect the depth of the architecture with the scale of the underlying like diffusion process, like or the kind of the underlying scale of the domain. And so this is something that we still don't have good understanding. And as I said, there's of course many algorithmic choices that have made a lot of difference in the practical side, in the empirical side. For example, how should I normalize my architecture? Should I add a residual connection or not? Should I have like a first should I have just like a convolutional model at the first layers and then have this transformer model on top, right? Transformers are just basically completely part of this blueprint, because they are basically something that you can define over a graph with kind of latent structure, right? Like a graph that is presumed to be fully connected. Anyway, so I guess that the point here is that here we have some framework, mathematical framework, where we can try to encompass many of the different algorithms and many of the different domains. All right. So I have a few minutes left, and I would like to spend them talking a little bit about some of the applications. And hopefully there will be time for questions if people have questions. All right. So maybe just one, and I guess that one of the things that I'm hoping to express in these applications is that it's not necessarily bigger is better. Like more layers is better, more parameters is better, right? There's actually a lot of interesting applications, in particular in computational science, where I would say like the essence, like the interest of these things is precisely on the other direction, right? And the fact that we can get very nice results with very simple ideas. And so here's some examples just to try to motivate what I'm saying. Here, think look at different areas of computation of physics, and we can physics is plugged with phenomena that has like a very complex spatial structure that is really non-Gaussian, right? And different instances of this phenomena, you can find them, for example, in turbulence. So the right physical model to explain turbulence is the Navier-Stokes equation. And as you can see here, the structures that you see are really non-Gaussian. Like if you look, for example, in statistical physics, in crystals, like Ising models or other forms of like spin glasses, they have also something that is really markedly non-Gaussian. And they, for example, there's this notion of like a critical, like phase transition, right? Like what is the temperature of the crystal at which the crystal really changes macroscopic properties, right? It goes from, having like a spins completely disordered to some kind of like order that emerges. Another phenomenon, another domain that is where this thing is super important is cosmology, right? So like if you want to have good models for cosmology, they really need to capture very clearly marked, important non-Gaussian structure, for example, like the creation of little, like aggregates of structures here, and so you want to be able to model them. And so really here we are in the business of setting up probabilistic models of this data, right? So how do you describe the statistics of this phenomenon? And so again, without trying to aiming to be like novel, right? This is really like a problem that has occupied physicists and mathematicians for on more than 100 years, right? And so a very natural, like a powerful class is to think in terms of Gibbs meshes. If you want to sound a bit more modern, you can call it energy-based model, right? So these are the probability distributions that are parameterized by some energy function. And so the question is really, how do you parameterize this energy function? Okay, and of course, how do you study or how do you manipulate these objects, right? Which are incredibly interesting, incredibly rich from both computational and statistical point of view. And so this is where, like, if I look at the problem of this form, where I start with a very simple energy-based model, where it would be basically I'm separating the energy can be parameterized by some parameters theta, but this parameterization is linear, right? So the energy is just a linear combination of what we call sufficient statistics. Okay, that's a very nice, it's called the exponential family. That's a very nice model that has a lot of interesting properties. And so, of course, the question is, how do you choose these sufficient statistics? So if you start from, again, like if you start from very simple sufficient statistics that would look like covariance, just look at the covariance between the input, then you are really in the Gaussian world, right? And this basically, this slide is hoping to convince you that the phenomena here is really non-Gaussian, okay? But now, let's see what happens if we replace this covariance by very simple representation that is just the scattering transform that I described before, right? So you just replace phi of x by the scattering transform. Okay, we just put the scattering transform there. And the scattering transform has very small number of coefficients, right? The number of coefficients is of the order of basically log n squared, right? Like n here's the number of pixels. And so here, what you can see is that the corresponding statistical model, still, the only thing that you need to adjust are this linear combination of scattering coefficients. And you can see that, okay, maybe it's not perfect, right? But look at the simplicity of this thing, right? There's really no complicated thing. There's no, there's no architecture search. There's no thing that you need to tune, right? You really get something that, in a sense, fundamentally captures something important about the physics, right? About the nature of this phenomenon, right? And so, and just to convince you why this thing can be useful, right, in the community, we apply this representation to some important problem in cosmology, which is called the weak lensing cosmology problem, like estimating some cosmological parameters. And that's joint work with Brice Menard and some of his collaborators and students. Brice is in Johns Hopkins. And so here, really, what you can see is that if you use this like scattering transform to estimate certain cosmological parameters, you can basically do, at least as good, even slightly better than a CNN, but with a very nice advantage that now we can perfectly understand what's going on, right? I mean, every scattering coefficient is constructed from first principles, and we can really relate it to something that is physical, right? We can relate it to some orientation, we can relate it to some scale, and really have a very small number of those parameters. And so that's something that is important and useful in many areas of science, right? In particular in cosmology. Here's another illustration that I wanna present. This is some ongoing project in collaboration with my colleague Laura Zana and Carlos Fernandez from NYU, and this is part of a very large team that we call the M-squared lines. And this is really the problem called the closure problem. Okay, and this is something that we use in the context of advancing climate models, right? We really want to use machine learning to improve climate predictions and to improve climate model. And so just try to present this problem for those of you who are not familiar. It's a very nice problem that is really at the interface of many things, right? In math, physics, and now machine learning. And so really the starting point is that you can describe many physical phenomena. For example, this Navier-Stokes evolution that, as I said, is a good model for what happens in the atmosphere. And so this is a phenomenon that you can describe it with a PDE, with a partial differential equation, that is defined over the space of all possible functions, right? So think about this X as a point in a three-dimensional or two-dimensional domain, right? So this is a function that, of course, has infinite number of dimensions, right? So that's a physics. The physics are, people trust the physics. The problem is that if I want to simulate this equation, I need to take this infinite dimensional space and somehow approximate it with a finite dimensional space, right? I can do that with a finite element method. I can use these Galerkin approximations. There's many techniques that we can use to take this equation and simulate in a computer. The problem is that because these PDEs are nonlinear, when I discretize the domain, the discretization of the domain does not commute with the operator, with the generator of the PDE. Right? So in other words, I cannot just simply plug the low frequencies here and pretend that the low frequencies follow the same dynamics. In fact, the dynamics for the low frequencies or for any kind of coarsened version do not exist. And this is what called in physics the closure problem, right? That you cannot close the PDE, right? There's not a closed set of equations that describe the evolution of the low frequencies. And this makes it like a very natural fit for like machine learning. Because now what we are going to do is we can try to correct, right? Basically try to learn what is the best dynamics that one could predict by of the low frequencies by basically introducing here an appropriate neural network. Okay, and this is actually, I mean, there's some very nice initial results by Laure and her collaborator. So the takeaway here is that in general, these architectures that we described, these geometric deep learning architectures, really have the ability to capture this kind of like a nonlinear scale interactions that are at the core of many problems that are, as you can imagine, of importance, very important, like it's actually an important problem to work on, right? Like to understand, improve this kind of climate predictions. Of course, there's many things that are still open. For example, how can we certify that these models do what they should do and they have a good guarantee? So that's still ongoing part of the project. Another thing that I wanted to mention is that sometimes there's this dichotomy between small models versus large models, right? Like a small model would be like the scattering, and large model would be the latest of the latest, let's say, vision transformer or something like that, right? So sometimes an interesting thing happens when you combine them in the right way. And that's something that we did in this recent work that is what's led by my student, Francis Williams, and some of my collaborators. And this is really the problem of surface reconstruction in 3D. So the setting is that you have some samples in 3D that are maybe just like a point cloud, and your goal is to output this 3D surface. And so the thing, the key idea that we do is that we really, I mean, here we are in the problem of trying to approximate a function, right? Like you can think this as a level set of a function, like this is like this implicit modeling, but this function is not defined as before in a space of dimension 1,000 or 1,000,000. It's defined over a three-dimensional space. And we are very good, we have very good mathematical tools to capture regularity, to define function classes of functions in 3D. In fact, kernel methods are incredibly good at that, right? So we don't need any neural network to tell us, to parameterize this function with a neural net. What we are doing is basically using a kernel for that, but the kernel has a bunch of free parameters that themselves can be adjusted, right? And can be maybe optimized for a particular data set that you have, right? And here, we basically use the flexibility of neural networks to precisely kind of think about this as I have some baseline kernel that is really expressing some kind of like a regularity that I'm hoping to capture. And then I can basically fine-tune this kernel using a neural network. And the results are very nice. Francis managed to get very, very nice results. You can see here that if you add this kind of neural network on top of the kernel, you can really improve upon something that was already very good, right? And you have a very nice generalization, as you can see here, right? I mean, these are objects that were never seen during training. So this is really like, it is an example that I like because it's a way to actually combine kind of good old technology, right? That is good for low dimensional regularity with something that is a little bit of this data-driven component. And the last example I wanted to present is this work that we are doing with a bunch of colleagues here at Courant, Ben Perher-Stoffer, Eric van den Eyden, and also Nick Boffey and Jigun Han. And so here really the problem is, again, is a problem that is classic in scientific computing, which is really the problem of simulating a PD, like integrating a PD. And this is an interesting example, because here we have a problem that we need to solve this equation, but we have no data, right? There's no data. The only thing that you have is the full knowledge of the physics. And so the point is that we are using the parameterizations that come from neural networks, right? So we are using the function approximation that comes from neural networks to find an alternative to classical algorithms for scientific computing, in that case, the Galerkin approximation. And really just to illustrate a little bit what this is about, here in the traditional like a finite element method, you would take this domain and I'll apply like a grid, right? And just try to basically approximate the solution as a linear combination of basis elements and just change the coefficients. Here we are basically representing the solution with a bunch of neurons, and we are evolving the neurons basically by putting the dynamics into the space of parameters. Okay, and this is interesting because we have a basically we can obtain interesting gains, especially in particular in problems that have a little bit of high dimensionality. For example, the Boltzmann equation, which is an important equation for kinetics, and also the Fokker-Planck equation. All right. So I think my time is basically off. So I just want to, bring home, insist on the kind of the conclusion and the main message that I try to convey today is that physical structure, like the fact that we have to learn with images, with molecules, with surfaces, with sequences. This is really like the key ingredient that we need to unblock the limitation of deep learning. In the sense that in absence of this structure, we know that the problem has no guarantees, right? That cannot have guarantees, right? It's like we are really cursed by dimensions. So we need to find the hypothesis in that space. And so there's actually, I think, an interesting set of prospects. We can use these models on a growing set of applications, right? Probably you have seen protein folding was elected kind of the science breakthrough of the year, and that has a lot of geometric deep learning inside. And there's a lot of applications, right? A lot of interesting things to do. But there's also like challenges, right, that we need to overcome, and we cannot just be happy with the numerical results. There's still like a lot of interesting questions on the mathematical side that we still should do better on. And I think we also need to be aware that if we ever need to integrate deep learning into the scientific world, like in the scientific computing, right? People using deep learning to solve actual problems, like maybe to design a new bridge or to design a new molecule. We need to have like a new drug. We need to have robustness guarantees, right? We need a little bit more robustness, and we need to do better in that. So with that, I want to thank all my collaborators that appeared in this work. Eric van den Eyden, Carlos Domingo, who is also from Barcelona, Ben Christopher, Stefan, John, Roberto, Soledad, Zheng Dao, Lei, Luca, Michael, Taco, Peter, Minjai, Ilias, and Brice. And thank you all for listening.
So thank you, Joan, for this very interesting talk. And now we have time for 1 or 2 questions among the audience. Okay. No question yet. So one of the questions that came to me is like when you define that different new architectures, they introduce some, sorry about this, some inductive biases, and then you relate like the different architectures, how to deal with symmetries. Do you miss any symmetry or inductive bias in the current architectures? Do you think there's room somewhere, some challenges in that sense?
Yeah, that's a good question. I mean, I think this is a good question that has been in the back, like in the mind of many of us, right, for many years, is that for example, without going too far, just take a pipeline of computer vision, like with the CNN. And you ask the question, okay, what is the actual symmetry that is encoded into this architecture? Obviously, the symmetry that comes to mind is something that has to be related with translation invariance, or maybe this like robust version of translation invariance that would be this near invariance to deformations. But in fact, we know that many problems in computer vision have much more symmetry than that, right? I don't know, you might have the object classes that some of them are going to be invariant to mirror symmetry. Some others are going to be maybe invariant to texture. And so there's many descriptions of symmetry that you could imagine that you can, if you encode them into the architecture, you are going to get like gains in sample complexity, but somehow you can still rely on, you can also rely on data to just memorize them for you. So maybe like a more geometric description is that if I have this orbit, right, like think about like the symmetries as, you know, like level sets of my function along certain kind of orbit, right, which is like the action of a transformation set. Of course, if you have data that you just sample points in that orbit, you can just forget that these are orbits, right? Just treat them as like more data points. And this is like the principle of this data augmentation kind of principle. So I think that the answer is that it depends what you want to do, right? If you want to prove things and basically get improvements in the sample complexity, then yes, I mean, putting more symmetries into the architecture can help you. But I think from a practitioner perspective, it's also true that kind of like the choice is not so clear, right? I mean, you can spend a lot of time fine-tuning architecture, and at the end, if you have enough data, this thing can be done for you. Clearly, there are symmetries that are absolutely clear. I mean, there was like a recent work, I think, on people who do this like scaling laws, and they really got different slopes for equivariant models than for non-equivariant models, right? So clearly, even at scale, you can achieve benefits by putting the right inductive bias into the architecture. That's absolutely out of the question.
Okay, so thanks a lot. I must leave it here, and so please let's give a big other round of applause to Joan. Okay, so now we just have 3 minutes break because we need to set up a little bit the call, and we'll follow with a Meta AI career session. So just 3 minutes and we will begin. Okay? Thank you, Joan.
Bye, everyone. Bye-bye.
D'acord. Sí, sí. I si no, els altres on són?
Que estic aquí retuitejant tot. Una foto molt bona amb els Pierre. Vine aquí, que ens fem una foto. Treu-te la mà per un segon. Treu-te-la. Anem al punt verd. Una, dues. Perfecte. Que si no ens donem el bombo i platillo i Meta fent de tot.
Molt bé, gràcies. Molt ben fet.
Bona tarda. Hola, hola. Que se'm sent?
Sí, com vulguis. Oh, no, anem-hi. Comencem amb el vídeo. I després parlaré des d'aquí.
We always ask, where is the future going to take us? But the real question is, where are we going to take the future?
There are no closed doors, no walls.
Holy mackerels, this is unbelievable.
We may have brain surgeons in Edinburgh operating on patients in New Zealand.
You'll send emotions, feelings, memories. Imagine a world where we are represented the way we want to be.
You know, in the future, it just feels like long distance won't be so distant.
That's a big frontier. Where do you want to go?
And we're just getting started.
Appreciate the past, utilize the present, but don't be afraid to create the future.
Javier, can you move? Hi everyone, I'm Pierre-Louis. I'm a research program manager for Meta AI, covering academic collaborations for the EMEA region, and I'm very pleased to be with you here today. First, we are proudly sponsoring this event for the second time. Last time was in 2019. And in these 30 to 45 minutes, we'll intend to open the doors of our research lab. We'll have a conversation with the researchers who are presenting to this event. I ask them to tell you about what is it doing research at Meta, and we are also with someone else who is remote online in London, Sarah Mohamed, who is a PhD recruiter at Meta. I don't want to lose time, so we'll have three parts. First, I ask Christian Canton to cover a broad presentation of research at, in AI at Meta. Then Sarah will cover careers. Then we'll have a short panel discussion with researcher and a Q&A session. Sarah, can you move to the next slide? Thank you. So, Christian, can you join me? Well, we are improvising a bit in this format. Huh? It's a relaxed conversation with all my distinguished colleagues here.
Thank you, Pierre-Louis. Welcome, everyone, again. So my name is Christian Kenton. I am a research manager at Meta AI. I don't know why I keep saying Facebook in my head, but it's Meta AI, just like keep it clear. So as many of you, once I was completing my PhD in this very same UPC, in this campus here, and I was starting my career as a researcher, and this was like almost 20 years ago. And nowadays, I'm pleased to be here to be telling you like how research has evolved since then for me, and how I can help you in your future. How can I, like Meta, provide opportunities for you to accomplish your dream, to do research, and to be successful in your careers. So, from my perspective, research at Meta, it's something very unique in the world. It's a place of action. It's a place of action in the sense that you will build research that will have impact into the world. And research at Meta covers the whole spectrum. So we have research that's like basic research in topics like computer vision, research like the one that you are used to do, work on a paper, work on an algorithm that has like some outcomes, have it published somewhere in a conference, in a paper. But also, you will have research that will go all the way to the product. So for instance, in my case in particular, I have had the opportunity at Meta to manage a bunch of teams where like research was the byproduct of the impact. So a publication were the byproduct of impact. So you think of something really hard to solve, a really hard problem. You aim to solve it, and in that journey, you will have research outcome papers. That's how it works in product land, for instance. So in this journey that goes from very basic research to like the research that is very close to the customer, there's like all the gradations of different types of research that you could do at Meta. Sorry, like my mask is killing me. For instance, we have like our FAIR labs. It's the place where like we have a lot of brilliant researchers. Some of them will be here talking with us today. They tackle the hardest possible problems, the problems that will make Meta successful now and in the future. We have a bunch of places in the world where we are having these research labs. In Europe, we have in London, we have in Paris, we have in Zurich, we have in Tel Aviv, and we have a bunch of other places where research is happening. Then you will have, as you move within Meta, you might have other opportunities that are not only in FAIR labs. In the past, we have like FAIR applied research, where it's like I started originally at Facebook, where your research is much more tailored to solve a problem. For instance, I used to work in an area at Meta called integrity. Integrity means trying to solve problems for our users. In particular, I was heading the team that was doing computer vision to tackle child pornography, terrorism, organ trafficking, drug trafficking. As you could imagine, this is a very applied research. It's not just like publishing something. It's more like, how can you use your computer vision algorithms to make sure that people will not be suffering the consequences of bad intent people? So that's more applied. Your research will be more tailored to a very specific problem, but it's as impactful as any other research. So the closer you get to the product, the more focalized will be your research. The farther away you have like research that might be more transversal, that can be applied across many places in the company. Many of you were asking me like, hey, when is Meta opening an office in Barcelona? I don't know. Honestly, I don't really know. I'll be the first one interested to move here. But something that has been made very, very clear for us is that Meta has the expectation to hire up to 10,000 people in the next years in Europe. So some of those 10,000 might be researchers. So there will be opportunities for you to work from Europe into our research facilities and potentially even remote positions. This is something that we've seen like blossoming in the recent years, unfortunately, through the pandemic. But that has opened a lot of opportunities. So again, research is at Meta, it's something pretty unique, not only because you have research that will have some very concrete impact, because also the amount of resources that you will have to do your research. I really remember when, a couple of years ago, we were doing this, a competition called the Deepfake Detection Competition, and we had to require a ludicrous amount of GPUs in a very short period of time. Something I cannot disclose, but it was like, this is impossible to have this amount of GPUs in one single physical place, and here we have it. So you have resources that are beyond your imagination to do research. That's also very appealing as a researcher. So I'm sure you will have a ton of questions, and I've been doing research, and I've been managing researchers and teams of researchers for a number of years at Meta. I'm happy to answer any question now or later on the Q&A. Definitely, it's hard to convey all my excitement for the kind of work I do when I support at Meta, but definitely it's a great place to start. It's a great place to grow and learn. Just to finish, one single thing that I remember very distinctly about Meta is the opportunity that you have to grow there. It's not just that you will do research with an amount of resources that is, unthinkable. I still remember when I joined Meta, I once went to our New York office, and I remember coming across Jan LeCun, and I was like, oh my God, that's the guy who invented deep learning. And I was just approached to him like, sir, can I chat with you? And he was very open, and we discussed ideas, and we built a GAN symposium within Facebook, and we're good friends, and we discussed things. It's like, wow. In many other places, you don't have the opportunity to have exposure to Turing Awards, to very accomplished researchers that will work with you, that will be eager to know who you are, and spend time with you. So it's something pretty unique. The opportunity to grow at Meta is something that I usually think of one of the critical aspects of our research community within the company. I'm sure I have plenty of questions. I'll be here for the rest of the day and tomorrow. I'm happy to answer more on how to apply our research ecosystem. We have internships, we have full-time research positions in a variety of places in the world. I let Pierre-Louis complete that, but definitely don't be shy, ask questions. We are here to help you grow. I'm personally happy to talk to any of you who might be interested. It's a great opportunity, seize it. I remember when I finished my PhD, there were no such opportunities. The research and corporate ecosystem was way, way smaller. I think you are blessed now with the opportunities that many others were not available, you had not before. So definitely think of how can you use that to just use it as a trampoline to do more and to achieve more, okay? Thank you very much.
Thank you, Christian. Sarah, can you move back to the previous slide, please? Thank you. I would make just a few comments on these slides. You can see here where are our labs in the EMEA region. And so we have the main lab in Paris, which is the third in size compared to the two big ones who are in Menlo Park in California and in New York. The third big lab is in Paris. Then we have the London lab, which is growing a lot these last few years, and then a smaller lab in Tel Aviv. I've listed here the institution we collaborate with close to this lab, because we have a research model which is based on a collaboration with the academia. It's really a strategic approach for us to have this mixed approach where we collaborate with the academia, with the network, very close to our labs. But of course, we are not just collaborating with ETH, PFL, because we have a lab in Zurich, or with CNRS, INRIA, or École Normale Supérieure in Paris, or UCL or Oxford in London. We are also collaborating with all other universities in Europe. I put a red dot here in Barcelona, and as you Later, we'll have this short panel discussion, including Roberto Desi, who is a PhD student here at UPF, and we have a collaboration ongoing here, and also in other university across the country and Europe. That's a very important model for us. Next slide, please. And also very important for us, for Meta AI, the model is based on open science and open source, very open, and that's the key aspect for collaborating with the academia. And we have these dedicated programs like the PhD internship program and PhD programs that Sarah will tell you more about. Can you move to the next slide? So I will leave the mic to Sarah to cover this career aspect in more detail. Thank you. Sarah, can you introduce yourself and start? We can't hear you.
My name is Sarah Mohammed, and I'm the PhD and Master's recruiter based here in London. Feel free to connect with me on LinkedIn. I am delighted you're spending the last hour with us. I know you had a whole day packed with presentations, so thank you so much for just taking up the time to spend the last hour with us. In this section, I'm going to discuss our opportunities available to masters and PhD students and what our interview process will look like. So currently on our website, we have the following roles open. So we have the research AI internship open, and we have research scientist full-time positions open. We have these positions open globally, which is the good news. So we have opportunities open in the US, London, Paris, Tel Aviv, Zurich, and we also have them based within FAIR and also FRL, so our Facebook Reality Labs as well. So please be mindful that we have tons of roles open, and as Christian said earlier on, we're going to be recruiting 10,000 people, so please listen up and hopefully you can find your place here at Meta. So at the moment, we are going to just dive into our internship piece for our current masters and PhD students. So that is 12 to 16 week internship for masters and PhD students. Interns should be passionate in areas such as deep learning, computer vision, audio and speech processing, machine learning, reinforcement learning, and applied mathematics. And at the moment, I think it'll be you guys will all be happy to hear that our internship will be looking to be in person from March onwards. And of course, we can't predict what will happen with the current situation. But the good thing is, you know, we have successfully executed a virtual internship for the last 2 years. So whatever the situation, we will make sure we'll adjust to it. But it's very important for me to highlight that we are looking to be in person this upcoming summer internships. For our internship, I really just want to dive in what it kind of looks like when if you were to, you know, come on one of our internship programs. So, of course, you will have tons of intern events to attend. It's a great opportunity for you to, of course, network with peers and build your network during your time here. So you will meet other researchers, you know, doing an internship, doing new grad positions and experienced researchers, and really just build your network there. You'll also be assigned a mentor during your time here. So it could be for a 12-week or 16-week internship. And throughout that, you'll have someone you can go ahead and reach out to overcome anything that's on your mind regarding your research or just day-to-day. When you join our internship program, you're actually going to be given a detailed project plan that we want you to really just kind of stick to aim for you to successfully finish your internship. And, and really what we're trying to achieve from the research that you're brought in to do. The goal is always, of course, to have a publication out of the internship. Now, of course, that is never guaranteed, but we do have all the resources and tools to try to make that happen. And ultimately also for you to get to know the meta culture, right? So hopefully the internship here will really just give you a full picture of how it is to work as a research scientist here at Meta. Now, the deadline for this is March 2022. So if you do want to go ahead and apply to that, please go ahead and do so. And I look forward to receiving your applications. So I'm going to move on to the next role here, which is the Research AI PhD program. Now, this is based in London and it is targeted at master's level students. And it's in collaboration with UCL and Oxford. So it is a PhD position for 4 years fixed term for PhD students in London who will work in collaboration with research labs at departments of computer science at UCL or Oxford, jointly supervised by academics at these labs and research scientists at FAIR. So ultimately, this is a great opportunity for current master's students who is interested in pursuing research, who is interested in while simultaneously achieving their PhD. So it is a 4-year program. And here the PhD is actually funded by Meta. So we will take care of all your tuition fees and you will also be receiving a competitive salary whilst working at Meta. So technically, you tend to have 2 supervisors, so one at the academic institution and one at Meta. And here, this is a very competitive program, but we really do welcome applications from everywhere. And for you to apply to this, we do expect you to, have a research proposal in mind. Who do you want to work for with? Who do you want to, kind of pair up with at UCL Oxford or at Meta? And what is the research problem you want to solve? So we are currently taking applications for that. So please go ahead and apply if you think, if you're currently a master's student and you want to pursue the world of research and want to pursue ultimately the scholarships with the PhD. We have a similar program, which I know Pierre-Louis just kind of dived into, which is the Research CIFRA PhD program. Now, this is based in Paris, but it's actually not something that is on an external link. And the reason for that is because to be eligible for our CIFRA program, and for those that don't know what a CIFRA program is, it is a PhD that is funded by the French government in partnership with the French government. And it's quite similar to the Research AI PhD program where we will fund your PhD for over 3 years, as well as simultaneously you working with our research to proceed with whatever research you're aiming for. And to be eligible for the CIFRA program, master students must apply for an internship. To go ahead and apply for our Research AI internship, master's internship that's currently happening in Paris. So that's a very high overview of our roles. But as Christian said earlier on, we're recruiting very heavily. Our goal is ambitious, it's 10,000. And so there's tons of roles globally. And one thing to just highlight there is you can apply up to 3 positions at any given time. So that's great. So 3 different roles at 3 different locations. In terms of the recruitment process, this is the timeline I would kind of suggest. So go online, apply online, submit your application, look for those 3 roles that are very suitable for you, those locations that you are willing to go ahead. And if you want to relocate to, of course, we are managing remote working as well. Go ahead, apply online. Once you've submitted your application, there will be a resume review where a recruiter will assess your skills and background in relation to the roles. And here, you know, I would really recommend that you kind of highlight the research you want to go into. Some people, of course, highlight the research problem they want to solve here at Meta. That's not completely necessary, because it is still a conversation we want to welcome when you come on site, of you know, bouncing loads of ideas with you as well. And you know, this is more for at master's level. You know, I get loads of questions saying, hey, Sarah, I don't actually have any publications on my resume, but I'm really interested in research. That's completely fine. We don't expect you to have publications at master's level. It's great if you do. But for that, just be mindful of the courseworks or the research or the project works you've done at university. You know, definitely put that on your resume. It's great to see what you're kind of diving into. If your resume, you know, there's a strong fit within our teams, there's loads of teams recruiting, of course, we'll then invite you to our one process, which is the final process. And that is a 45-minute round of coding interview, and then a 45 minutes of a team match conversation that you will have with the team. In terms of the team match conversation, I'm going to dive deep into this. It's really just to get to know you. Understand a bit more, you know, your motivations around why Meta, why the research. And, you know, it's a great opportunity for both parts to actually share ideas of research and what it would look like for you to come in, and what you're trying to solve. So it's a great conversation. And I always say an interview is a two-way thing. So hopefully we'll be able to match you with the right team and the right research. And of course, fingers crossed, it all goes well and you'll be having an offer. So, you know, as I said, our applications are open. We are hiring aggressively for our internships and new grad positions. So feel free to go ahead, and hopefully I'll connect with you on the more of the recruitment side. So feel free to take our website down, if anything, for you to just look at later. But thank you so much, and I'm going to pass it over back to Pierre-Louis to kickstart our panel.
Thank you, Sarah. I'm sure you have plenty of questions, but we'll take the question just after the next part of this session. So I'm calling Javier, Roberto, and Albert to join me here, and we'll have a short conversation. Thank you. So we have here three distinguished researchers, I would say, at different stages of their career and in different labs and with different roles. I think it's interesting to ask them who they are and why they what they do at Meta first. Albert, when did you join Meta, and what are you doing?
Okay,
so yeah, I know you presented a talk this morning, but briefly from your role at Meta.
Yeah, so I recently finished my PhD, so I did all my studies here at the UPC. I studied here at La FIP.
No, it's me.
Then I also did my master's here, and I also did my PhD here at the IRI Institute. And yeah, during my PhD, I did an internship at Meta, so I like it very much. So just when I finished, I just decided to join, and I joined at the beginning of this year, so I think in February. And I'm based on Zurich at Reality Labs.
Thank you. So you're based in Zurich. Roberto, you're a PhD student, right?
Yes, I'm a PhD student at UPF here in Barcelona and Facebook Meta AI Fair Labs in Paris. And I joined 2 years ago, and I started my PhD 2 years ago.
Thank you. So we explained our model where with our PhD programs in Paris and in London mostly, but in fact we can have some exceptions, and Roberto is a perfect example of the exception we make. I see is doing his PhD student here at with us and with UPF. And Javier, tell us about you.
Sure. So I'm Javier Romero. I did my PhD in Vision for Robotics in Stockholm, KTH, a few years ago. After that, I did a postdoc in MPI Perceiving Systems in Germany. And 5 years after that, I joined a startup, which eventually got bought by Amazon. I spent 3 years there. Until this summer, which is when I joined Meta, at the time Facebook, Reality Labs. My situation is kind of funny one. I am working with the Pittsburgh lab for Facebook Reality Labs, but I'm working from Barcelona. So I'm working remotely from Barcelona to the team in Pittsburgh.
Okay, thank you. So we are all different situation, and with Christian based in Seattle. I have a question to Roberto. Because you are doing your PhD, when you were a master student, you had to take a decision. What was you could have been looking for a job very easily with your track record to work into a company or a startup. Why deciding to do a PhD, to start doing research when you were in Italy?
So yeah, I was doing my master in Trento, and the master that I was doing, which is a master in cognitive science, was very research-oriented. So it exposed us to many aspects of research. And when I decided to do research, I realized that I wanted to learn all the different aspects of doing research. So I think what we saw even with all the work that has been presented today is like research is a very collaborative process. So there are many skills involved, going from coding, theoretical backgrounds, so theoretical aspects and proper like studying the topic to writing the papers. And I decided to do a PhD because to me, it was a perfect chance to like dive deep in all the different aspects of this research process. And I like the PhD at Meta because it sort of exposed to like both sides of the research aspect. The industrial one, so you are exposed to like doing research at the industrial level at scale. So at Christian said, like research is very massive, so you can do research that is really like a huge impact, but also with a focus on the more academic, basic, pure research aspects. And the reason why was that I knew that I wanted to do research on the whole aspects of all this process, and not only applied research, not only theoretical, and I think the PhD sort of lets you explore all different aspects within the 3 years' time, and try, fail, rewire, and learn. So I think a suggestion for like master students is like, it's good to understand whether you are interested to do the entire process, or maybe you want to specialize to be more applied. So maybe like something like a research engineer career would be a better fit, or maybe you would like to do only like software engineering part. So I think understanding early during our studies, during our master course, what we want to do is like a key aspect to make an informed and good decision why we would decide after for a PhD or not.
Okay, thank you. A question to Albert. You transitioned quite quickly from being a PhD student to becoming a research scientist. In the academic world, the transition is most probably to do a postdoc or to do various postdoc before before getting a job or being assistant professor or whatever. What do you think? That's a quite accelerated career at that stage. What do you think?
Yeah, so I feel like now it's becoming more and more popular that once people finish the PhD, they move directly into like research, but in a company. I feel that there's not much difference between doing like a postdoc and going directly to like companies like Meta. At the end of the day, we are always doing research. So I guess the main difference is that in a postdoc, you're expected to have like students and you'll work with your students. And instead on these sort of companies, you work more like people that also like are just researchers. But you still do like research and everything. So it's not that different.
Okay, thank you. And an open question to Javier and Albert. You are both at the Reality Labs organization, and compared to a Fair Labs and AI, Fair Labs is more kind of open academic model research organization. Reality Labs is much more focused on, as the name explains, virtual reality, augmented reality, all these aspects on that sort. The metaverse at the horizon. What do you think about that between open-ended basic research driven by curiosity or research driven by a clear goal and to land and to impact on products? I'd like to get your opinion also, Javier.
Sure. So first, I should say that even within Facebook Reality Labs, which is something that I know a little bit better than FAIR, there is quite a bit of a landscape in there of different levels of basic research in a sense versus applied. When I joined, or more than basic research, sometimes it might be better to differentiate it in terms of timelines. How far in the future you're looking to apply your research to a product or not. Because as you said, Facebook Reality Labs is more focused on a particular application. People do not come with a random idea for a paper and implement it. It has to be related to the topic. But there are labs which are focusing on a relatively short-term timeline, and there are other labs which are focused on a relatively long timeline. And you can work on something that is focused, but that it might be something that won't be solved maybe in 5 or 10 years. When I joined Facebook Reality Labs in Pittsburgh, one of the reasons that convinced me to join that lab was that it's a lab that is also very open in terms of publications. Not all the groups are as open, but this group publishes a lot. It's publishing very good papers, and the timeline, the problems that they are facing are extremely hard. The motto or the goal of my team is to create a communication experience in virtual reality that is indistinguishable from reality, physical reality. So you can imagine that that is not going to be something that is solved in 6 months or 1 year. That is not something that you will solve only with engineers. You have to do a lot of research. You might call it basic or not. It's focused on a particular problem, but it's long term. So you can choose, even within Reality Labs as well, whether you want a longer timeline or you want something that you can see applied into product earlier. And what I would say the difference is more on how focused you are on a particular problem. In this particular case, virtual reality, something that relates to that topic, or you want to be a little bit more open-ended. Both are interesting. In the past, while I was in MPI, my research was a little bit more basic. We had this topic of, okay, well, you can think of your papers and work on them. I like a little bit of focus on a particular topic because right now at least, because it brings very good talent on that specific topic to the team. Like one of the things that I also like about my current position is that you have world experts on this particular topic in a group, which, as far as I understand, sometimes it might be difficult to get in basic research because it's sometimes might be a little bit more individualistic. You have different groups. In Reality Labs, it's very clear that in order to achieve these big, practical but challenging goals in the long term, you need a strong team that works on these, which has different parts of engineering, long-term research, short-term research, and all this.
Thank you.
Yeah, so to add to that, I totally agree with Javier. So for me, the main difference is that there it works more on like fundamental problems. And then in the case of Reality Labs, now it's been publicly made public that the full focus of Reality Labs is to build a metaverse. And that, of course, no one knows how to build a metaverse. There's a lot of super challenging research problems there to be solved before we can have this metaverse. So the main goal of Reality Labs is basically doing research on making this a reality. So yeah, I would say that's the main difference. But at the end of the day, both are research.
Thank you. I think you may have many questions, so maybe it's time to go to the Q&A session and leave you asking questions to your attendees. Christian, can you come back with us? We have a second microphone too. Is there any question in the room?
Here is one.
That's a somewhat technical question. So on the job listings on LinkedIn, the remote jobs, are they? What exactly do remote and hybrid mean? Is it remote from any place in the EU? Is it remote from any place in the EU from day one? What exactly does hybrid mean?
Sarah, can you answer to the remote aspect of working at Meta? You're muted.
Can you hear me?
Yes.
It's a great question. So at the moment, we are growing our remote locations day by day. So there are tons of locations that we are open to remote, and there's majority of Europe now, which is covered. So we have changed our format of recruiting people. So you can now, if you want to go ahead and, move forward with a fully remote position, you can now move forward with that. So you can go ahead and apply for whatever location, and you'll start noticing that it will say London and remote. And that is open to anywhere in Europe that you would find comfortable to really just be at your best and enhance your productivity. And every day we're actually adding a new location, which is great. So we're not there yet in terms of the perfect remote model, but we are definitely open to it now.
Thanks. Any other question here?
Could you tell me which were the most difficult questions in the selection process for 3 of them?
Excuse me, can you repeat?
Can you repeat?
Could you tell me which was the most difficult question in the selection, the process selection for the PhD or for your entrance in the Meta?
What? So you mean technical question or?
Yes, it should be. It's.
Yeah, okay. So, I think that we cannot say the exact question each got.
Yeah, but...
I think that's... But in general, I can say in general.
Yeah, I mean, when you are in front of to the team, it's so difficult to do the selection of that.
Yeah, sure. So first, like the types of questions you'll get, they depend on the role you're applying for. So at least in my case, for research scientist, I got like a couple of coding interviews and then a couple of research interviews, and then one behavioral, and then also one to like present the work I had done in the past. So it really depends on your skills. I feel like as researchers, if, for example, if you've done a PhD, like you've been doing research for a long time, so that's one of your strong parts. And normally, the coding part, it's where people normally struggle more, and it's like the one you have to prepare the most. And it's basically like algorithmic questions and data structures.
So let me add, so in the selection process, the coding is the part that you can prepare the most. So I interview a lot of people every week, and like coding, I tell them, prepare. There's like tons of resources online. Your recruiters will provide you with resources to take a look on. So that's the part you can prepare. Algorithmic, there's going to be a bunch of things that you can prepare on. Your research, you are probably the best and most prepared person to answer questions about your own research. So probably that's the part that you already are prepared for that. And finally, for the team matching, or I mean, psychological assessment, I don't know how you want to call it, it's more like behavioral, trying to get to know you, how you think, how you solve problems, how you work with others. That's something that we also evaluate, and this is very important. You cannot prepare. I mean, it's like, I'm going to ask you, for instance, how do you solve a conflict with one of your colleagues? And you will have different stories from your background or your previous experience that will allow us to understand. We'll ask questions. I mean, something I want to say that the process of recruiting process is extremely fair. I've been doing that for 5 years at Facebook. It's extremely fair. And it's like, you can prepare as much as you can prepare. The rest is what you know, what you already are the expert on. So don't be nervous for it. I mean, definitely and Sarah, you probably also can comment on that. It's a very easy process in the sense that it's straightforward. We've been trained to make you comfortable on that. And definitely you want to be successful. Really, we want you to be successful. So I think coding is the part that you can prepare the most. The rest is just think about, you are the expert at that. Be comfortable.
Thank you. I'm just going to add in here, first of all, apology, I actually lost connection during your question. So that was a great answer, folks. And I think just to add on to that piece, we as recruiters want you to succeed as well. So when you do join our recruitment process, you will receive tons of preparation from us. Well, not tons, but you will receive, really solid preparation links from us, good advice from us. And we're here to help you through the process. So if something is unclear regarding the coding piece, or even the team match conversation, feel free to just follow up with your recruiter, and they will go ahead and dive into that a bit more. And we do prep calls. And as Christian just said, our process is not there to kind of trick you guys or anything. It is a very quick process, it's a 2 interview for 45 minutes, and it's really just to see your passion and authentic side towards research, and of course to be able to see if you can solve the the problem at hand. But we give you tons of resources, so hopefully when you do join our process, you will see that as well, that support.
There is a question here.
Hi, so cool presentation. I was wondering if any of the panelists could walk us through one case where some research that you worked on ended up being in the product, in the Facebook product, and how was that process? Like, how do you coordinate with the product teams, with putting in production that algorithm or that approach, A/B testing it, etc.? And well, if you can be specific, that's great. Otherwise, as specific as you can be, that's super interesting.
I don't have examples for Meta because I joined not that long ago, but I can talk about my experience in Amazon, if that's the best we have in the panel. Or, well, Christian, you probably have lots. You probably have lots of examples in Meta.
Yeah, I can
go for it.
So you were mentioning how your research may end up in production?
Yeah, for example, what you were mentioning before about
Yeah, so for instance, like I can comment on like the, comes to my mind, like the deep fake detection challenge. So we're trying to generate, I don't know, a gazillion examples just to provide a data set for the community. Something that we did, and you just like might take your research and try to build it in production, and that has its challenges. Like one of the classical challenges is whatever you built in your lab setup will not work, never, in production. That's by default, because the distribution of the world outside, it's very different than the data that you have. For instance, we're like doing detection of deepfakes. The world is very big, so there were a million different cases that we've never seen before. So there's always an adaptation phase on how your research needs to be tailored for the practical use case. And that's like a lot of work. There's a lot of data munching, a lot of data understanding. Then also like what are the parameters that you are optimizing for? What is the complexity, the latency? What are the requirements for the product team to put that algorithm in production? And that will be also another constraint. But I would say there's like a lot of fun from like, yes, I published a paper at CVPR and it works very well, like let's build it into this thing, like it doesn't fit, it doesn't work. That's where like a back and forth with product teams works. I'm sure there's like other examples, but it's always fun.
Cool, so I understand that there is a deep fake detector in Facebook, for example, now that initially by research, right?
Ish, I cannot confirm or deny that there's anything, but I would say like there could be like some people build a detector, you try to train it with some data, you try to put it in production, and the false positive rate just skyrockets. Like, why is that? Because the world is very different. So this, I mean, adaptation of your like lab setup to the real world where you're processing trillions of faces and videos and whatnot, it's going to be, I mean, daunting. So definitely there's like an adaptation process, and that's what usually like drives a lot of time in just bringing things in production.
Okay, thank you so much.
I would like to add one last thing to that. Apart from the preparation phase, which is very different because, as Christian said, the data you encounter in the world and the robustness that you require is very different from the paper. There is something that it wasn't obvious to me before going to industry, which is that, while in academia you typically prepare your data, write your algorithm, write your paper, and you're done. You can move on to another paper or continue a follow-up, but having in mind a new paper. In industry, you have this next stage, which you might be involved or maybe other people are involved, which is in checking how it's working, adapting it in the future, and trying to improve it based on the signals that you get from how people are using it. And that is quite different from academic research. It's a totally different kind of signal, trying to use this feedback loop, trying to see how to get reviews from people and use them to improve your product, or how, if there are no explicit reviews, well, maybe people are clicking more one or another, and how to use to improve your product. All that process is something that is not that present as much in academia. It's also very interesting.
Cool, thank you.
Is there any? It will be the last question because it's 5
all
to
the
7.
pressure. It's really amazing. 10,000 people hiring. I mean, this is an amazing endeavor. And I saw all the topics on the left: internship, food positions. Everything was there except natural language processing. So, is this because this text is considered old Facebook newsfeed, and vision and audio is new Facebook, multiverse, metaverse?
So I'll just go ahead and take that. So thank you for noticing my own error on my own slide. We do hire within NLP, and we have a strong base. We're here within London and the Paris lab. So we're definitely hiring within NLP, within the internship space, and also within the full-time research scientist positions. As I said, we have huge teams doing this type of work within London, Paris, and Tel Aviv, and Zurich. So I put my hands up for that error, but NLP is definitely something we're hiring for.
Thanks. I think we can, Sarah, we'll close the session. I don't remember if there is a last slide. If you have more questions, maybe you can just write Sarah or myself. We'll give you our email address in the last slide. And
actually, so I'm going to be sending you guys all an email out by tomorrow with all the links of our jobs and just mine and Pierre-Louis' email address. So look out for that as well.
Thank you. And thank you for attending. Thank you.
Hey, okay, so just a super quick reminder, tomorrow we start at 9:30, okay, with the panel, industrial panel. Hope you enjoyed the first day. See you tomorrow.
Vols veure això? Vols veure els coquitos que hi ha per aquí? Bueno, l'ordinador el pujaré per fer un cas, que no sigui dit.